They're using a tap. Two. Two. Check. Check. Check, check. Check.
Okay, we're going to start in like 30 seconds, so if you'd like to take a seat and break. Okay, so I wasn't not exactly 30 seconds. We're just a little, one or two more AV problems, but I'm probably going to start. Okay, so my name is Michael Doggett. I'm one of the general co-chairs with Hugo Cole, who goes up the back. And welcome to High Performance Graphics 2026. I'm very pleased to see all of you here. It's great to be back in LA. Those who've been to SIGGRAPH a few times, been in LA many times, but this year we are at a slightly different venue. We're not at a downtown hotel, but we're relatively close to downtown, so I hope this is working out for everyone. So we're happy here to be here at the USC Hotel. And the room that we're in is the Grand Ballroom, so you all found your way here, which is great. And the breakfast and the lunch will be served in here. So you can see how the breakfast is served, lunch will be much the same. The banquet will be nearby. As we go through the slides. And we can continue to stream on YouTube, but I don't think I'm actually on YouTube right now. We're working furiously to get that up and running before the first paper session. And YouTube page is well visited. Recently upgraded videos to HD from last year, so that was really nice. And previous years were all stored up there, so that's a great resource that the conference is providing. So a little bit of history for those who don't know it. The conference has been running for many, many years and traces back to what was your graphics workshop on graphics hardware. And you're doing the slides. You see, 1994, that's when I read my first paper, this first time I went to graphics hardware. So I've been involved with the conference for many, many years. And the conference in its current current forum started in 2009. And there have been many changes with publishing. At the moment, we publish our papers in the US, in ACM, in the CG Journal, and when we're in Europe, we publish with the Computer Graphics Forum. So we're still switching between the US and Europe. And so what we're about as a conference technically is innovative algorithms, efficient implementations, and underlying technologies. And I think this has been true through all of time, and I expect will continue for some time forward. So algorithms is important both to industry and academia. And the underlying technology, we've always had a lot of involvement from the silicon industry and associated industries like the game industry and, for example, Adobe as well. And then the way that this gets presented, this kind of combination of academic and industrial, is through the keynotes, the papers, and the Plot 3D. So it's a bit of a combination. It's not strictly academic and not strictly industrial. The way we run the conference socially, so it's the opportunity to talk about ideas, to find new collaborators, and to interact between employers and employees. So certainly for my personal career history, all my jobs, except for my first one after my PhD, have come through people I've met at HPG. We have long breaks, so we have a long lunch break, and the idea is it's an opportunity to talk to the people here. So if you see people present, I encourage you to go and talk to them. That's a great way to meet people, to find out what they're working on, and to find common interests. Okay, so now we're going to move into the fast forward part, and I'm going to get different chairs from the conference to come up and talk about different aspects. And of course, we're going to start with something that's very important that pays for all of this is our sponsors.
So I got to be sponsorship chair this year, and conferences like this are not cheap, and we have a good set of sponsors this year. It's a bit less than we've had in some past years, so if anybody is interested in supporting the conference, particularly in future years, I'd like to invite you to contact me or anyone on the committee, and we'd be happy to take your money to help reduce the costs for all of the attendees. But as you can see here, NVIDIA stepped up this year to be our top tier nurturer sponsor, and then we have our solid set of sponsors here in the middle. And as always, we're very grateful for all of our sponsors. You'll see their slides rotating between sessions, showing a little bit about the companies and what they've got going on, either at HPG or at SIGGRAPH. And yeah.
Thank you, Joseph. Thank you. Okay, and now a little bit about the papers.
Thank you. So I'm Christoph. I'm one of the two paper chairs this year. Markus is not here this time, but you can find me if you have any questions. And we have 14 accepted papers this year, which are distributed across 5 paper sessions. Every paper gets a 25-minute slot, so we have talks of around 18 to 20 minutes. And this year, all presentations, not just for papers, but in general, are in person. There's nothing remote or pre-recorded. I think that's great. So you can find all the speakers here and talk to them throughout the conference. And these 14 papers were selected out of a total of 40 complete paper submissions. And this selection process would not have been possible without our excellent International Papers Committee. You can see all of their names here. So all the reviews for the papers have been done by the people on this list, and we owe them tremendous gratitude for putting in all of this effort, for providing constructive feedback and enabling us to make good decisions. So please, everybody, let's have a big round of applause for our IPC. Now, I'll be saying a few more things about the review process tomorrow in the town hall session. For now, the important thing is all of the papers are available for you to look at. They have all been published in the journal Proceedings of the ACM on Computer Graphics and Interactive Techniques. You can find them under this link or via this QR code, which is the same link. And also, if you look at the schedule webpage for HPG, the individual papers are linked there as well. And something new this year is that all of the papers published by the ACM, including our HPG papers, are open access. So that's the transition to ACM Open, and that makes things so much easier. We no longer have to hunt down author versions or distribute papers separately during the conference. It's all open access under Creative Commons licenses. And in fact, the papers have already been online there 2 weeks ago, so everybody had some time to look at them ahead of the conference. Thank you.
Okay. And now Andrew's going to say a few words about our 2 keynote speakers.
Hi, I'm program chair this year. So about our 2 speakers, we have first this afternoon at 3:20 to 4:20, we have Patrick Cozy and Sean Lilly. Patrick is the chief platform officer at Bentley. He's also the founder and CEO of CCM. And Sean leads 3D software development at CCM. Both of them are key contributors to 3D tiles and the GLTF standard. And they'll be speaking on the complex models and simple solutions. Basically, they'll be sharing the evolution of 3D tiles for streaming, rendering, querying massive heterogeneous 3D models by bringing together simple solutions, or simple-ish and well-known data structures. And then discussing the open source kind of collaborations they've had on that. And then tomorrow afternoon, we'll have Eric Lindholm. He was a senior distinguished architect and master inventor at NVIDIA before retirement. He's had key contributions to the invention and the evolution of the GPU, including sort of co-architecting some of the first GPUs. He'll be speaking tomorrow. And on his talk, the first half will be kind of a retrospective on the development of graphics pipelines and the GPU, and then the second half will be looking forward to what might be coming. So.
Okay, so there are our main sessions, and now we'll talk about some of the other smaller sessions we have. So the poster session and the Hot 3D, sponsor sessions, student competition, and the town hall. So tomorrow, just after lunch, in the sort of second half of lunch, we'll have something we call the town hall. It'll be in this room, so it'll be hard to get away from. You'll have to leave the room if you don't want to hear it, where we get people in the community to talk about the conference, what they like, what they don't like, what they want to change, and we sort of look for people who would like to help with organizing the conference. And the banquet tomorrow night, and then on Sunday we'll have an awards session. So first I want to talk about the poster session. So the chairs were Sebastian Herzog and Michael Kern, and there are 3 posters, and you'll be able to see the 3 posters. They're just outside in the hallway. I see some of them are up already, but then we'll have a dedicated session tomorrow, and it's during the coffee break. So the idea is that you grab coffee, and you can go out and have a look at the posters, and the authors of the posters are there to talk to you. Another thing we have is a student competition, and the student competition is run in Shader Toy. So we give students some objective, and this year we focused on proceduralism and global illumination, and these 5 entries came in. And if you have some time and you want to check them out, the QR code for the Shader Toy page is on the web page. So have a look on the web page, and you can go and have a look at them. And then on Sunday, Ashkay will be here to talk about the different entries and pick some winners from these. Okay, so Hot 3D. Holger's going to tell us all about it.
So hey, I'm the Hot 3D chair this year. So we got 3 full sessions this year round, which means 6 talks. And I think we have a range of interesting topics from, so they range from extending the Slang shading language to execute neural networks, to GPU advances in GPU architecture, to optimizing neural networks for GPU execution. We have 2 talks about new tools that help you debug or profile Vulkan applications on Android. And we have a final talk where they basically pose a more general question about the future of research with regards to real-time rendering for games. So I hope you'll find all these sessions interesting, and that's it from my side.
And then to tell us about the banquet details, here's our local arrangements chair, Will Usher. Come on up, Will.
Yeah, so the banquet is at the USC University Club. You can go to it by Google Maps. This is just showing you it's a short walk on campus. So if you go off campus, you're going the wrong way. The important thing to mention, if you requested dietary restriction, the banquet manager will be there and will give you a note that you can give the server or the staff there to make sure you get the appropriate meal. If you didn't request a specific dietary restriction meal, don't take those cards because they are for the people who requested them. We have to order a specific number of plated meals, so we want to make sure that everyone gets what they asked for. And during the buffets, the dietary requirements for each meal will be listed on a card in front of each item. So, yeah.
Okay, so to wrap up, I want to say a big thank you to the organizing committees. There's a lot of work from a lot of people. This goes on all year. In particular, I'd like to point out these little 3D printed HPGs. So they're like our gift for this year, which was generously printed by Andrew Garrard. So we thank Andrew for that. If you've noticed, one is an uppercase and the other is a lowercase character, and you randomly got one or the other. And if you really need to change case, then feel free to go to the desk and see if you can swap. Another nice thing we have are these badge stickers. I don't know if you've been at SIGGRAPH a while, you've probably seen these. So this is kind of like free advertising for us. You put on your SIGGRAPH badge and you can wear it at SIGGRAPH. So please do that as well. I don't have time to go through everybody, but I'm very thankful for everybody's effort in making this conference happen. And if you're interested, please come to the town hall. If you're interested in joining the committee, you can talk to me or the respective member of your company who's already on there. But yeah, please do reach out if you're interested. Okay, so enjoy the conference. We'll go straight into our first paper session. Here comes our paper chair. And our speaker.
Do you know, by the way, if there's that other mic somewhere for audience?
Yes, I will go and track it down. Okay, our first speaker.
It's like Jacob Heisel.
Okay.
Yeah. Hi, welcome to the first session we have. It's on our first session is on accelerated ray tracing, and we have 3 papers in the session. And for our first talk, we have one on memory efficient bounding volume hierarchies with merged nodes by Jacob Heidel, Jem Yüksel, Eric Brunwand, and Andrew Kanzler. And Jacob is presenting, so please come take it away, Jacob.
If you prefer, we also have a minus one. So the should have to be quite close.
I think this is good.
Take whichever way you want.
Is this plugged in? Hello? Sorry. Okay, cool. Looks like everything's working.
So yeah, my name's Jacob Heidel, and then today I'll be presenting memory-efficient bounding volume hierarchies with merged nodes. So starting off with the motivation for this, it comes from a simple observation, which is that hardware ray tracing tends to be memory bound. It's very easy for us to scale compute, but it's much harder to scale memory access, or memory bandwidth more specifically. And so on top of this, a lot of traditional BVH formulations optimize for compute rather than memory. And so this led us to a question, can we change this? Can we update these BVH formulations to actually optimize for memory access rather than compute? And yeah, the answer is yes, we can totally do this. And if we do it, we can both optimize for less total memory access, so each ray reads less data from memory, and we can optimize for a smaller total BVH footprint, which reduces cache pressure and DRAM access. And furthermore, our simulations show that this does actually provide uptick in performance. And so that's it. Thanks for coming to my talk. All right, I'll give you a little bit more than that. But let's back up for a second and talk about bounding volume hierarchies more broadly. So this will be the traditional formulation of a bounding volume hierarchy that most of y'all are probably familiar with. We have a binary tree with axis-aligned bounding boxes, and these bounding boxes allow us to very efficiently cull large parts of the scene. And crucially, this turns ray tracing from a linear search to a logarithmic search. And at the scale that we're generally doing ray tracing, at the scene scales that we generally have, this can lead to orders of magnitude better performance, even with a naive BVH implementation. Of course, we don't use naive BVH implementations. We can do much better, and we do. Most of the major hardware vendors at this point have some variation of compressed wide bounding volume hierarchy. And the way this works is we convert our binary tree to a wider tree, so generally between a 4 and 16-way tree. And then we take the child nodes and we lift them into the parent node and we quantize them. And we quantize them on this local grid, which is a lossy operation, but our bounding volumes only need to be conservative, and so this is fine. And what we get in return is obviously a large reduction in both memory footprint and total memory traffic. Again, that was our stated goal, so this is great. However, there's one problem, and the problem comes when we talk about how we actually represent the primitive data. So traditionally in graphics, we represent meshes with an index buffer and a vertex buffer, and this is great because it eliminates vertex duplication. And that means that the actual data, the actual mesh, is much smaller in memory. However, when we talk about ray tracing, this has a major downside, which is that this index buffer requires indirection, and when we access the vertex buffer, we do it in a way that's very incoherent. From our tests, we see that when we do this, it's actually really bad for memory performance. And other people have figured this out as well, and so we can do a little bit better than this. And the traditional way of solving this problem is that we store triangle pairs instead. So by storing triangle pairs, we can read all of the triangle data in a single transaction. We can align it to 64-byte boundaries. And because they're pairs that share an edge, we can reduce some of the vertex duplication. However, when we do this, we still have a lot of vertex duplication. And because of that, our memory footprint is really high. And so this is where our BVH comes in. So what we did is we replaced our traditional triangle pairs with a small, what you can think of as a little meshlet. And this meshlet, or this primitive block as we call them, contains a little index buffer and a vertex buffer. And this vertex buffer can store up to 9 vertices. And what this provides is really an intermediate point between having a full index buffer, which removes all of our vertex duplication, and having just triangle pairs, which eliminates only a modest amount of vertex duplication, but allows us to do a single transaction. In this case, we can still read this whole data structure in one transaction. It's 128 bytes, and it's aligned. And this index buffer only references local vertices, and so we don't have any of this global indirection that we're trying to avoid. The problem is that when we do this, this actually makes things worse. And the reason for this lies in the surface area heuristic itself. So the surface area heuristic is at the center of most optimized BVH builders. And the way it works is that we estimate the cost of a node in the tree by its surface area as a fraction of the root node surface area times the cost of visiting that node. So the area gives us an estimate of the probability of visiting the node, and the cost function tells us how expensive it is if we do visit that node. And so if we can minimize this heuristic, then we can minimize the cost of the tree In other words, we can create a tree that's better. The problem comes is when we talk about the way that the surface area heuristic traditionally represents leaf cost. So if we look at C leaf here, we can see that the cost of a leaf node is proportional to the cost of intersecting a primitive times the number of primitives. And it's really that second part, the number of primitives part, that becomes a problem. As the number of primitives grows, the leaf node becomes more expensive in the eyes of the BVH builder. And because of this, a good BVH builder will rarely build leaf nodes that have more than a handful of triangles. And if we do this and we add our new BVH representation, what we end up with is all of these really empty leaf nodes. And so we're just paying for these 128 byte blocks that we're not even filling up. So to address this, we restructured the surface area heuristic to make it reflect memory access rather than compute. And what that looks like in practice is that the cost of visiting an internal node is now the size of that node, so the amount of memory we have to read to visit the node. And the cost of visiting a leaf node is the size of our primitive block times the number of primitive blocks that are needed to encode that leaf node. It's usually 1. And the really key insight here is that doing this requires you to tell your BVH builder something about the target format that you're going to encode this BVH in. So that's the theory behind it. What does this look like in practice? So I've drawn a sort of representation of a traditional BVH pipeline. You start with a cluster of triangles, and you organize those triangles along some space-filling curve. And then we take that space-filling curve, and we use it to construct a binary tree. This is the classic LBVH algorithm. And then after we have an LBVH, we can do other things like reinsertions or agglomerative clustering to further optimize this tree. But what all of this is really driving towards is reducing that SAH cost. Once we have a binary tree, like I said, we want to have a compressed wide tree. So we need a way of converting that high-quality binary tree to high-quality compressed tree. And to do this, I like to think of it in 3 phases. The first is that we're going to take our leaf nodes, which currently just contain a single triangle, and we're going to collapse them to form larger leaf nodes. And we're going to do this in a way that doesn't, or that reduces the SAH cost, or at least doesn't increase it. And then after we've done that, we can go ahead and convert this binary tree to a wide tree. And this is, there's several ways of doing it. I'll talk about it later in the presentation. But suffice it to say, we convert this binary tree to a wide tree. And then finally, we can compress it. So we can encode it in the target format. So to make that a little bit more concrete, we can talk about some methods for doing this. And the first is dynamic collapse, or this is what I call it. And this is a collapse that uses dynamic programming to compute the cost of all the different permutations of collapsing this tree. And once we've done this, we have this giant cost table. We can just traverse it from the top down, and we can realize the tree that minimizes our cost. And so what this looks like in practice is we have some binary tree. We traverse bottom up to compute this cost tree. And then we traverse top down, and we replace nodes to form wide nodes. And that cost tree tells us how to do this. So we just choose the cost, or choose the way of collapsing that minimizes the cost, which is baked into that cost tree. Then we do the same thing for leaf nodes. So once we reach a node where the minimum cost is to form a leaf node, we go ahead and form one. And we do that until we've traversed all the way down the tree, and we now have our wide tree, which we can compress. Now, let's take a look at what this looks like with our memory-based SAH function swapped in. So once again, we compute this cost tree. Only when we compute the cost tree, we use that cost function that I described earlier, where we compute the number of blocks we need to encode a leaf node, and that becomes the cost of that leaf node. And when we do this, what we see is that we form primitive blocks directly during our collapse, and we also form primitive blocks that are much larger than we would have otherwise done. And that's because we're not penalizing the builder for inserting more triangles as long as it doesn't cause us to spill over into a new block. And the net effect of this is we get really high quality trees that optimize for both memory footprint, but also the amount of data that we actually access during traversal. Now, that's one way of building BVHs, and it's very good, but it's quite expensive to produce these cost trees. And so sometimes we also want a faster method for building these trees. And for that, we have introduced what we call the greedy collapse. I mean, this exists in prior work, but we've extended this to work with our new cost function. And this is great for real-time builds, which require us to rebuild the BVH either every frame or every couple of frames. So the greedy collapse starts off with a bottom-up pass as well. And in this bottom-up pass, we're just going to try to accumulate leaf nodes in an SAH-friendly way. And so if we can, we continue up. If we can't, then we terminate, and that becomes our leaf node. In the second phase, we're going to traverse top-down, and we're just going to take the bounding box with the largest surface area, and we're going to pull it up into, or pull its children up into the parent node. And we're going to do this until we've reached the end of the tree and everything has been pulled up into a block. And then we can encode our primitives just like we did before. With MSH, the algorithm looks very similar. The only difference is now we're going to directly try to encode these primitive blocks, and we're going to keep going up the tree until we've filled these blocks. In other words, we can't take two siblings and merge them into the same block. And so once again, we get much fuller blocks doing this, and then we can do the same top-down collapse that we normally would do. Another sort of interesting thing falls out of this memory-based SAH formulation, and that's that we can do things like primitive block merging. So what that means is when we have our final tree, even though we've aggressively pulled primitives into these blocks, we can still end up with sibling blocks that were not completely full because they weren't SAH friendly. And because we're representing cost as the expected memory cost, there's actually no cost for us to merge two blocks together. When we visit a node, we're always going to read the block that it points to. And whether or not that block contains 4 triangles or 2 triangles doesn't matter. And so that's what we do. We take 2 sibling nodes that point at different primitive blocks. We take those primitive blocks, we encode them into a single block, and we point those 2 nodes at that block. And crucially, we do this without updating the actual bounding volume itself, which means that this doesn't increase the MSAH cost of the tree. Moreover, we can do the same thing with interior nodes. So we can take sibling interior nodes and we can combine them while preserving the original bounding boxes. And when we do this, we also can create new opportunities lower down in the tree. So in this case, we can also merge these 2 blocks together. And one of the really cool things about this is that in our BVH representation, we only need a single bit to encode this. And that bit just says either point at the next primitive block or point at the previous primitive block. And in other words, you're merged with the previous primitive block. And so this is really friendly to still obtaining good compression rates in our tree. So that's the theory behind our memory efficient bounding volume hierarchies. Let's talk about how we actually evaluated this. So we tested our BVH across 5 different scenes and 4 different ray distributions. So for our ray distributions, we used primary rays, reflection rays, mirror reflection rays, diffuse GI rays, which we call secondary rays, and second bounce diffuse GI rays, which we call tertiary rays. And then we measured traversal performance on arches, which is a cycle level simulator that I presented last year. And we compare against the state-of-the-art compressed wide BVH, which is a 6-way compressed wide BVH in 64 bytes with triangle pairs for the leaf nodes. And what we found is what I said before, which is that if all we do is switch this BVH format without updating our builder, we actually pessimize performance. So things get worse. And this is because we have those really empty leaf nodes that they can encode up to 8 triangles, but instead they're only containing a couple triangles. And now the blocks are larger, whereas the triangle pairs fit in 64 bytes, our blocks are 128 bytes, so things get worse. Once we introduce these build methods that I presented earlier, we actually see a pretty sizable increase in performance, which comes from a reduction in memory traffic during traversal, but also in BVH footprint, which reduces cache pressure and DRAM access. So diving in a little bit deeper, it's a big table, but I'll walk you through it. If we look at, again, this is our data structure with traditional build methods. we see the problem, which is that we only produce 1.3 primitives per leaf node on average. And that's nowhere near enough to actually fill these blocks and make them worth having. Again, you can see that here from the large primitive footprint. And also, we make the actual memory access during traversal worse as well. And of course, this translates to worse performance. Using just the dynamic collapse alone, we can see that this mostly resolves the issue. We end up with much better primitive block fullness, and it translates to a much smaller tree. Obviously, partly because we just simply have fewer bytes per triangle, but also a little bit less obviously because we have fewer internal nodes now. So you can see our total internal node size dropped from 9.1 bytes down to 2.9 bytes per triangle. And this does actually translate to better traversal performance. And then we see a similar thing with the greedy method, with the main trade-off being that since the greedy method just tries to accumulate large blocks, it's very good at producing full primitive blocks, but it does so at the expense of producing slightly more memory access during traversal. And that causes it to perform slightly worse. And then furthermore, we can add merging on top of both of these, or all three of these methods. And this further reduces the size of the tree or the memory footprint. And it does so without increasing the amount of memory traffic that we produce during traversal. And so we go slightly faster than we would otherwise. The other thing we were sort of interested in is this trade-off between block size and the amount of memory access you do during traversal. So if you have smaller blocks, then reading each block accrues less memory access. But the larger your blocks are, the more reuse you can get. And so larger blocks tend to be smaller in memory, but accrue more access during traversal. And so to that end, we tested 64 and 128 byte blocks for both primitive blocks and node blocks. And what we found was sort of interesting, which is that the optimal point for each is different. And this is where the combined 64 byte node blocks and 128 byte primitive blocks come from. And then the other goal was to compare dynamic collapse versus greedy collapse. These are CPU build numbers, so take it with a little bit of a grain of salt. But what we see is what we expect, which is that the greedy algorithm is significantly cheaper to build than this dynamic approach. And so just to summarize, we reformulate the SAH cost from being a compute-based SAH to a memory-based SAH. We then present a new data structure, which we designed around optimizing for this memory-based SAH. And we present methods for actually constructing trees that are optimal, namely the greedy and dynamic collapse and merging. Finally, we evaluate with cycle-level simulation to show that these theoretical benefits of reducing memory access actually translate to real traversal performance. And that's it.
Thank you, Jacob. Do we have any questions from the audience?
Good morning. Okay. What are the downsides?
Increased compute. So let me go back to this slide. Oh, my slides aren't up anymore. All right. Yeah, the short version is increased compute. So one of the things about having larger leaf nodes like this is you do need to intersect those leaf nodes when you visit them. And so instead of, say, reading 2 triangles and needing to intersect 2 triangles every time you visit a leaf node, now you have to intersect 4 or 5 triangles. And so if your compute pipeline can't absorb that, then this ends up not really being worth it. But there's actually a really interesting like intermediate point, which is this idea of using the traditional SAH for your collapse method, but then doing merging on top of that. And this allows you to actually have a tree, which is that compute optimized tree, but encoded in a much smaller memory footprint through merging. And so if you are compute bound, then that's an option. But that's the main trade-off is when you optimize entirely for memory access, you do so at but you sacrifice compute.
Great talk. So when I play it around with this bottom-up collapsing stuff, I always find it difficult to kind of quantify the amount of memory that you need to propagate state up the tree.
Yeah.
Essentially, can you comment on how much data you need and worst case stuff? In particular, if you build it in parallel, right? You have to allocate for the worst case.
Yeah. So I have two thoughts on this. One is that there is a trivial case lower in the tree. So every time you collapse upwards to form a larger primitive block, you need to evaluate whether or not that's possible. That's really what you're doing, and then also the surface area. But the primitive blocks can trivially encode up to 3 triangles. So until you have 3 triangles, you don't actually need to try to encode that primitive block. And really all you need to know is the actual vertex data, which is going to live somewhere in memory. So in terms of propagation, you could imagine that after you reach that point, you start propagating the actual encoded blocks themselves. That prevents you from having to re-encode them later. And all you have to do is try to merge 2 blocks together, which should be a cheaper operation. Or you could just start from scratch each time, but then you incur the cost of reading data. So yeah, I guess the main cost is just transporting these blocks up the tree. Yeah. Sorry, I was just kind of thinking out loud there, but hopefully that answered your question.
I think we had time for one more question.
The paper calls out that it might be tricky to implement in hardware. What are the challenges there? The building.
It might be tricky.
To implement the BVH building in hardware. It's a note at the end of the paper that I saw.
Yeah, I think what we were just saying is that was, it's not conceptually tricky. The tricky part is mapping this all efficiently to warp-based execution is really what it comes down to. So like, how do you very efficiently try to merge 2 of these primitive blocks together while getting good warp utilization? That's really all it comes down to.
Thank you.
Next, let's give a big hand to Jacob. For next paper, we have ray tracing massive amounts of animated geometry by Holger Grun, Carsten Benthin, Michael Kern, and David McAllister. And Holger Grun is presenting. So take it away, Holger.
Just a second to unlock my computer. No. Let's see if you recognize this one. Yeah, okay. Let's present. Okay, my name is Holger. I'm presenting our paper on ray tracing massive amounts of animated geometry. Actually, I think we should be a bit more precise. So the way I'm going to present is mainly aimed at, or very good at, animating uniquely deforming objects. That means objects that have their own independent animation. So it's not a case where you reuse a certain animation state across the scene a lot, but you can really uniquely animate every object. And we're also targeting non-rigid animations here. So something that's rigidly animated, there's good ways to do this already. Okay, just a recap. I guess everybody knows this, but why is it expensive to ray trace many uniquely animated objects? It's actually not the ray tracing part that's usually the slow thing. It's about building and updating all the acceleration structures that you need to build in order to ray trace the scene. So very simply, first of all, you need to animate the vertices, which is sort of clearly the cost scales with the number of vertices here, but then you also need to write them to memory, which can be quite costly. If you have dense geometry, you're writing all the geometry to memory into a buffer, so there's lots of bandwidth involved here. And then, of course, you need to feed that updated vertex buffer into the BVH or BLAS update or rebuild, depending on what you want to do. And that, I mean, is costly as well. The compute cost scales with the number of triangles in the BVH, and the memory cost in sort of the same way it scales with the number of triangles in the mesh. So if you have lots of uniquely animated stuff, you can see that the compute cost can get really high, and the memory cost can get really high as well. And then at the very end, of course, you update the top level acceleration structure with all the bottom level acceleration structures you've built. So just a simple scene here. We've picked an object that's quite dense in terms of geometry. So it has like roughly 400K triangles and I think 250K vertices. It's a skinned object, so we're skinning it. We're updating the BLAS. It's basically an updatable BLAS for a dynamic geometry, and you can see here that obviously the build times get, high quickly, and so does the memory cost. You can see that at some point this becomes intolerable in terms of cost for a real-time scene. And of course, people have dealt with this problem for a long time since the event of real-time ray tracing. So there's lots of techniques to deal with this to some degree, but in the end, none of them fully avoid the per object cost if you want to uniquely animate lots of objects. So on the application side, of course, you can pick a lower LOD if things are far away. If you can tolerate that, that's great. Low BVH complexity, less build time, lower memory footprint. Then you can do like staggered BVH updates. Some applications do that. So you can say, hey, I only want to spend that much time per frame to update BVHs. Then you build a priority list, and you only do the very important ones first, and then perhaps some things that are further away, you just update them every few frames, if that's okay. Then a lot of work has gone into making BVH builds faster. So new algorithms, so things like HBlock. And then there's lots of work or lots of progress on the API side for building things. So NVIDIA has done a lot of work here. So you can now basically have a petition TLAS where you only update the petition that has dynamic objects. That saves a lot of time. And if your content is ready for it, you can also use cluster level acceleration structures, which allow you to sort of decompose an object into smaller parts. They build nicer, they can be updated nicely, and you can only animate the part of the object that needs animation. So this is good stuff. But I mean, the uniqueness issue is still there, right? If you have 1,000 objects and they're all made from clusters and they all in a different animation state, you can't reuse the stuff. So the problem sort of remains, right? This is just, it stays. And then, of course, GPU makers have been trying to reduce the memory footprint of BVHs. We've just heard Jacob's talk, so along those lines. So the idea of the paper is really, really high level. It's basically to say, hey, let's animate a coarse proxy instead of the real geometry. So we don't animate every vertex. And then the idea is basically, in our case, we use a tetrahedra cage that we use to wrap the object, and we animate just this cage. And this was actually inspired by an HPG talk that happened last year. It was, I think, I pronounced this properly, from Luton et al., who basically looked into using tetrahedra cages to animate and deform non-mesh-based objects. So we are taking that to the ray tracing world in terms of like, how do we map that to BVH structures and so on. So our BVH, as we will see, is basically has just the complexity of the cage. So we decouple the BVH complexity from the complexity of the geometric complexity of the object itself, which means low BVH build time and low memory footprint. We also, in the same way, decouple the animation cost from the geometric density of the thing, which is definitely nice, right? I mean, who doesn't like lower costs everywhere? But so yeah, this is the thing. A couple of things to say here. Why are we using tetrahedra? That will become obvious in a short while. Basically, is the key thing is that you have a rest space tetrahedron, that you build over the rest space of the object that you want to animate. You have an animated tetrahedron in the animated cage, and both things are linear, like both tetrahedra are linear, so concepts. You can build a mapping between the two, and we'll see how that is used later on to do this, to ray trace this on the hardware. And obviously the quality of the cage, or the complexity of the cage, is the quality not for performance, but also for animation quality, because if you have a really low-res cage, it perhaps can't capture all the nice animation detail you need. Okay, so what do we do in our paper? We have a really very simple cage builder. The way it works is this: you put a bounding box around the rest pose of the object. We subdivide that into voxels. We throw away the empty voxels. Then we tetrahedralize the voxels, the remaining ones, and then we throw away the empty tetrahedron. Then as a last step, we clip the mesh to each of these tetrahedra in the cage, which results in sort of mini meshes or meshes. So one mesh is just the part of the mesh that's inside one of the tetrahedra, and they're shown in a color-coded way here. So each color-coded patch is one mini mesh and belongs to one tetrahedron in the cage. So then, once you've done that, there's probably an offline step you've done, right? You compute the cage and the mini meshes offline. So when you start up your application, what you want to do is for each of the mini meshes, you want to build one, I call it mini BLAS, but it's just a normal BLAS, or can be a normal BLAS, for each of these static meshes. You end up with as many BLASs, static BLASs. They are built once. You never need to animate them. We'll see how that works. And there's one of those BLASs for each static clip mini mesh. Okay, now we just animate the cage, right? And all is done. Okay, so the question is, of course, now if we have the animated cage, how do we get to ray trace the deformed object? So the way this works is sort of this, and this shows sort of a geometric approach. So on the left-hand side, this is one animated tetrahedron of the guy, of this, little human here that's animated. And you can see that basically this animated tetrahedron, there's a world space array that intersects the tetrahedron. So there's an entry triangle and exit triangle. And for each of the triangles, we can basically note what are the barycentric coordinates of the head points. And then you take the barycentric coordinates and transfer them to the rest pose tetrahedron, which gives you a rest pose ray. And by tracing the rest pose array, we basically ray trace the animated deformed tetrahedron. So we deform the ray and not the geometry. And as it turns out, and that's quite obvious once you think about it a little bit, is that each tetrahedron has like three independent linear vectors that are linearly independent. So they form a coordinate system. Well, you can change between coordinate systems. You can just build a matrix that goes from like animated tetrahedron to rest space tetrahedron. We're going to use that to animate our array, or to deform our array. So this brings us to the animation pipeline, or the BVH update pipeline for this type of animation. So first of all, you animate the tet cages, which means updating just the vertices of the tetrahedral cage. Then we compute for each of the tetrahedron in all of the cages. We build an instance transform that's outlined here at the bottom of the slide. I don't want you to read this now. It's detailed in the paper, but believe me, it works. And so you compute this transform, and then you basically create an instance description that basically, uses the transform for exactly one tetrahedron, and then it points to one of the mini BLASs, right? So this one basically points to the mini BLASs, and we put all these instance descriptions that point to all the mini BLASs into the TLAS and update it, and then we can just trace the array. It will go through all the different instances and transform the array, and by that sort of deform the geometry implicitly. So how does that look in terms of like the XR PVH structure? So the hierarchy looks like this. Obviously you have the TLAS or the PTLAS, and then you have like, for each cage, you have a number of instances. One instance for each tetrahedron in the cage of the object. So you see here you have like a lot of more instances in the TLAS, but then you don't need to build any BLAS anymore, right? Because they all reference the static mini BLAS we've built. So I can have 1,000 objects animating, they all reuse the same mini BLASs. It's just the instance transform that I changed to basically make these guys animate independently. Okay, and obviously, if you do that, and we've done this for the same scene with the frogs and so on. So we've tested I show here like two tetrahedral configurations. One uses like 1.9K tetrahedral per frog, and the other one uses 5.5K tetrahedral per frog. And you can see here that, well, obviously in terms of memory bandwidth, I mean, it's obviously a joke, right? I mean, it doesn't compare. I mean, memory bandwidth is very, very low in this case. And the same is true for builds. I mean, build speeds are also high, so build times are low. Obviously, the more complex the cage, the more you sort of go towards the build speed of the BLAS. But then you also have to think about the fact that you're touching a lot less memory, right? Okay, where it gets a little bit more interesting is when it comes to ray tracing this thing, so traversal. You can see here that it is usually the fastest way to trace the BLAS if you can fit all of those into memory and if you can afford to build them all. But you can get reasonably close if your cages are sort of modest size, if that can work for you. But yeah, it's more expensive to ray trace this stuff, and that really doesn't come as a big surprise because in the end, we are putting all these instances in the TLAS. The TLAS builder puts a bounding box ABB around this thing, so we have a lot of overlap between these ABBs, so traversal is going to be slower. That's not a surprise that a BLAS traverses faster. I'll probably build one. But now, I mean, we're assuming you're in a situation where you are build time limited or memory limited, so overall frame time you still win, right? Even if the tracing is slower, at least for our test case with like 2 rays, and on this hardware configuration, you win. Right, it's a lot faster. Okay, so this slide, I hope it plays back okay. So that shows on the left-hand side the video we've uploaded with our paper. It shows a scene with, I think, 4,000 grass patches. They all have high geometry, like dense geometry. I think we have like 64 trees and 64 animated characters. So that amounts to like 580 million polygons, and we're animating the scene in like 10 milliseconds. So I think it was around 2 million tetrahedra that we're updating. On the right-hand side, you see a tree that has 1.1 million triangles, so there's no alpha testing here. So it's sort of a hero tree model if you get close to it. And it's actually animated through a bone animation that is driven by a wind simulation. But what we are showing here is basically the tree animated through 1K tetrahedra, so 1K tetrahedra cage. And you can see it captures a lot of the fine details of the animation. So it's totally doable for some types of animations to replace them by tetrahedral approximations. Okay, so where does this leave us? I would say use it where it makes sense, right? So there are situations where it's a clear win. When you are memory limited, when you're BVH build time limited, it's going to gain you a lot if you can use it, right? If you're happy with the animation quality. So for things like plants swaying in the wind, perhaps distant or mid-distance crowds of things, and sort of animation LOD for sort of all types of objects, right? If you can live with the approximation, because that's the thing you need to be aware of. Clearly, it is an approximation of the original animation. It's not a replacement for every hero asset. There's a water tightness issue in theory because like when the ray goes through the scene, the ray changes for each tetrahedron. It's a different ray. And where the tetrahedra meet, there's no, I mean, we're dealing with floating point numbers, right? So there's no clear guarantee that there's no water tightness issue there. We've worked around this in the paper. It works okay, so I think it may not be a big issue. At least we haven't seen any issues with it, with our workaround. And then, of course, there's some offline pre-processing you need to do. You need to build the cage, you need to clip the mini-meshes, and so on and so on. Okay, so what do we want to do in the future? We're looking into hybridly animated objects. I mean, it's very clear, right? If you know that the deformation error is high in some part of the object, you could then just properly animate that mini BLAS and then join it with the rest of the tetrahedral object. You can have a hybrid object that works okay. We want to build better tetrahedra cages. In our case, the bone animation in our case works by just copying the bone config of the closest vertex to the tetrahedral vertex, that's obviously just a crutch, but it works okay in our case, so we can obviously optimize that, right? The bone assignments for cage vertices to minimize for deformation. We want to look more into cage LOD, how that works with like transitioning between LODs. We want to look into how multi-level acceleration structures can speed up the builds, because in the end, if you have a TLAS, the quality of the TLAS and how you build it, it would be either trace fast or either build fast. The same thing is true for partition TLAS. So the MLAS, if you stick basically all the instances of the animated object into one mid-level structure, it's sort of, the build flags can be different for that one. So you can sort of isolate your updates from the rest of the TLAS and you end up with a lot less instances in the TLAS. So that's going to be interesting. We're also going to look into how PTLAS and CLAS works with all of that. And then we want to find a new water tightness paradigm that allows us to make sort of mathematical sound watertight solution that runs fast. A quick peek. If you're worried about building these tetrahedral cages, we're currently working on a header-only C++ library that can do all of this stuff. So if you're interested in that, come and talk to me. Yeah, that concludes my talk. I think we have time for questions.
Any questions from the audience?
The algorithm that you were showing for the creation of this tetrahedralization was rather non-adaptive.
Sorry, I can't hear you properly.
The algorithm to generate the tetrahedra, was it really adaptive? It was, if I got it correctly, a uniform grid. But if you have a character model, for example, the hands are going to have much more complexity in their animation than the upper part of the body. So
Yeah,
do you have anything more adaptive there?
Well, this is part of the stuff we're doing right now is obviously you can, if you know, you can measure the animation, or the deformation error over, let's say, all the keyframes of the skinned object, and then you can adaptively split the cage and give it more detail where there's more deformation error, where the object bends more, stuff like that. It's all possible. Mm-hmm. And yeah, we've got some of that working.
Great, thanks.
Thank you.
Is self-shadowing all correct?
Can't hear you. Is the mic working? Still can't hear you. Sorry, I don't know what's going on.
Is self-shadowing always consistent?
Sorry, I really can't hear it.
Does this work? I think the question was, is the self-shadowing consistent?
Self? Oh, self-shadowing. Oh, I see. Well, yes. In the end, right? The shadow would, of course, represent sort of the deformed shape you get. Yeah, that works. That just works. Because every ray would go through the same cage and the same deformation, so that works fine. Yeah. You can do a lot of, if you really want to, let's say the objects in the skinned objects are now seen. What we did is we did actually pick up the skinned normal of the thing and use the skinned normal to light the thing. So you can do that. But then, every normal can just go through the transpose inverse of the, matrix. The matrix isn't orthogonal anymore, but as long as it's not degenerate, that works. There's no problem there.
Hi, great talk. How does the tetrahedra change with meshes that change their level of detail? Like for meshes that are really far away that become proxies, does the tetrahedra also become proxies for that?
Yeah, that's a good question. This is something we're working on at the moment as future work. So the thing I would say at the moment is just, if you have like continuous LOD, it's a different thing. But if you have like separate LODs, you could just say for that LOD, I'm going to build. In the end, right, you could build a lower resolution cage. You could use the same cage, and then, of course, you need to find out when to switch. So If you want to reuse the animation quality, use a lower res cage. Otherwise, just use the same resolution cage on the lower LED object. That just works. Yeah.
Great talk, thank you. Have you looked into making the approach also compatible to blend shapes instead of bone rigging system? I know that for facial animation, blend shapes are still widely used in games. Do you see compatibility here? Any secret sauce? Thank you.
Yeah, that's a good question. So like, let's say, for example, like morph tags for the face, stuff like that, right? So yeah, I mean, the thing is, that goes into this one thing I mentioned, like hybrid objects. So it's totally doable to basically isolate a portion of your object from the tetrahedralization cage, and you can then just animate that portion of the object properly. The only thing you need to take care is that where it basically touches the cage, you need to basically then snap the vertices on the border of the cage to the points where the tetrahedral cage wants them. So at the seams, you need to adhere to that, but it's doable. Yeah, I got a prototype working that does that. It's not too complicated. I mean, among all the other things game developers do, they do terribly complicated things, so that's not a complicated thing.
So I have one concern about numerical precision, right? When you have transformation matrices, if the thing is far off or at a high coordinate thing, you have very small rotations, and then add those to huge offsets, possibly huge offsets. Usually that's not a problem if an entire object is transformed, but for you, every individual tet is transformed. So shouldn't you be seeing some kind of through shoots and gaps between how the rays get differently transformed between neighboring tets if you move the thing away?
Yeah, you can see them, right? You're totally right. I mean, if the tetrahedra, any of the tetrahedra becomes like, either degenerate or if it gets like squashed too much, then some of that whole thing will sort of collapse, right? So you need the tetrahedra to be reasonably well behaved. So that this again may put another limit on your animation. And yeah, it's described in the paper, so definitely you can see these gaps. It's not watertight. So the way we work around this at the moment is before we clip to the tetrahedra, we sort of augment them for the clipping so we have a little bit of overlap, right? But that is no guarantee for watertightness. So this is something we're working on at the moment. But in our tests, it has worked okay. And it's probably a model dependent, sort of epsilon you want to use to generate these overlaps.
Thank you, Holger.
Welcome.
For the third and last talk this session, we've got common subtree merging compressed opacity macromaps by Thomas Chernak, Jaina Modisette, and Marcus Bilater, and Thomas Chernak is giving the presentation. So please take it away, Thomas.
Hi, I'm Thomas Chernak from the University of Leeds, and with my fellow PhD student Jaina and supervisor Marcus, we wrote a paper on compressing opacity micromaps. Let's begin with some motivation. This is a scene that we used as part of our evaluation. After instancing, there's about 5 billion triangles in this scene. 2 billion of these triangles are alpha tested, which gets us nice, good edges on our leaves. But we can ray trace this in real time, but it's a little bit slow. Alpha masking slows down our intersection testing when we're ray tracing. For every single intersection with a triangle that might have an opacity mask, we have to call some user-defined code in the AnyHit shader. This probably involves fetching the indices, then the UVs, and then sampling the texture. Our ordered ray traversal of hardware ray tracing was we might have many of these tests per ray. Opacity micromaps were introduced to speed up intersection testing with alpha masked ray tracing. They've been implemented in hardware on the latest NVIDIA GPUs, And the people behind Indiana Jones and the Great Circle claimed up to 50% speed up to their main path tracing pass when using opacity micromaps. We've contributed a lossless compression method for opacity micromaps, which maintains similar performance to the current method. We've added a level of detail scheme for our method using an aggregate hierarchical opacity, and we've applied all of the same compression method to standard binary alpha textures. Let's begin by looking at the scene. We're going to zoom in and see the resolution that we can provide. So this entire scene has just 5 megabytes of opacity data in total, and it's faster to ray trace than standard alpha textures. This is the regular triangles in the scene, and as we zoom in, we're going to see the micromap wireframe. Here's our aggregate hierarchical opacity in action. On the right, the sampled opacity from our data structure is used to alpha blend, and on the left is the standard high-resolution opacity micromap. It's hopefully visible, but there's less aliasing on the right. So how do opacity micromaps work? They use microtriangles to encode opacity information. Here, the large triangle over that leaf is a real triangle from the geometry. It's been subdivided twice here using a uniform edge splitting, which produced 16 microtriangles. We could subdivide it as many times as we want. Each of these subtriangles is then labeled. For a two-state mask, they're either labeled transparent or opaque, O or T. Then, when we hit a triangle, we can then convert its barycentric coordinates to a micromap index and sample the micromap value. If we sample opaque, we'll confirm the intersection. If we sample transparent, we'll reject it. But this is a low-resolution two-state map. But if we were to use this directly, we'd end up with quite a jagged edge on our leaf. The four-state micromap introduces an unknown state. When we encounter an unknown state, we can fall back to our standard high-resolution methods, such as regular alpha testing. There's two unknown states, unknown opaque and unknown transparent, which lets a four-state map fall back to a two-state map. There are some drawbacks to opacity micromaps. They give us a nice speed up, but they come with a memory cost. High-resolution micromaps are too large to use. 1 million micromaps at 10 subdivisions is 122 gigabytes of information. We see that many use cases of opacity micromaps tend to use lower resolution, four-state opacity micromaps. The people behind Indiana Jones and the Great Circle, again, said they used up subdivision 6 four-state opacity micromaps. Even then, 1 million triangles at subdivision 6 is a gigabyte of memory usage. I'm a PhD student on a PhD stipend, that's too much. The implementation of opacity micromaps in modern graphics APIs does reduce memory consumption below this a bit. An indirection stage is added with some metadata which allows triangles with identical micromaps to share memory. Foliage is a main use case for opacity micromaps. Foliage is likely to have duplicate leaves across a single mesh without instancing. The sponsor tree only actually has one texture across all of the leaves. The indirection stage also allows different triangles to have different levels of subdivision. This means we can focus the resolution where we need it. Some triangles don't need a micromap at all. A triangle in the center of a leaf might be uniformly opaque, and we can just denote this with a special pointer. Let's see how this reduces the storage in the bistro scene. This is the standard method still, not our contributions. At subdivision 7, it goes from 390 megabytes of memory usage to 9 megabytes of memory usage. And at subdivision 10, it goes from 25,000 megabytes to 580 megabytes, with about half a megabyte of metadata. This means there's only about 4,500 unique micromaps in the entire scene, despite 200,000 uninstanced alpha-mask triangles. Even then, 580 megabytes is still undesirable, so we seek to compress this data. We take inspiration from the SVDAG data structure. It's a binary compression method for voxel data using common subtree merging over sparse trees. Let's see how common subtree merging works. This binary string might be an opacity micromap for this leaf. We can build a tree over this information. We've used blue to represent ones and and gray to represent zeros. But we don't need to represent these zeros explicitly. We can delete them and recognize that their value will be 0 by their absence. And we can propagate this up the tree. Now we have a sparse tree representation, we can merge common subtrees. If we take a look at these blue subtrees, they're all identical data. They have one child to the left and an absent 0 child to the right. They're identical data, so we don't need to store it 3 times. We can just delete 2 of them and redirect the pointers. These green subtrees are also identical. They have one child to the left and one child to the right, and we can deduplicate. Now, we can go up a level. These orange subtrees are identical. They've got a blue subtree to the left and a green subtree to the right. It's the same piece of data, we only need to store it once. Now we have a more compressed piece of data. We might have more than one micromap. A use case is opacity micromaps, and we have many micromaps on a single mesh. And since they're on a single mesh, they're probably going to be resident in memory at the same time, so we can compress them together. We can merge common subtrees across micromaps, which might be for different leaves. Here, we can recognize that we've got another blue subtree, and we can just delete this one and redirect the pointer over. Here, these two peach subtrees are identical. No child to the left and a child to the right. Finally, up another level, we see a blue child to the left and a green child to the right, and we can delete. Merging common subtrees across different micromaps here has given us just 2 nodes left over. We can also merge common subtrees across different meshes, but that will depend on your implementation, because as soon as you're compressing together, they've got to be resident in memory at the same time. Let's build a tree over this micromap. We're building a 4 tree here, and it's sparse, so we're not representing children of empty triangles. Each triangle points to a child, and we've colored common subtrees the same color. If we look on the far right here, all of the blue triangles are the same. They've got an empty child on the bottom left, and the rest of the children are filled. We can deduplicate that to get much less data. So SVDAG traversal uses common subtree merging, and is done in real time on the GPU. You can get tens of millions of rows per second. Opacity micromaps are simple to encode in a 4 tree. Every time we add another subdivision level, we get 4 more children. We do, however, maintain the space filling curve of the current method. But 4 bits are tricky to align. We might use a bit mask to represent which children exist for a node. So we use a 16 fan-out. This has the great benefit of giving us a shallower tree of half the depth, which makes it faster to traverse. We pack all of this into an array of 32-bit integers. Each node has a 16-bit child mask, and for each child that exists, each 1 in the child mask, we have 1 child pointer, 32-bit child pointer. At the leaf level, instead of child pointers, we simply use a leaf mask of the final values. And this is 16 bits, since we have 16 children. Since it's 32-bit aligned and we have some 16-bit elements, this leads to some padding. So if we have an odd number of leaf masks, we're going to have 16 bits of padding afterwards. But more interestingly, at every single level, we have a 16-bit child mask. And before that, we put 16 bits of padding. In this padding, we choose to store a 16-bit aggregate hierarchical opacity, which is simply the percentage of children which are opaque. We can use this similar to a bitmap to reduce aliasing. All in all, the 32-bit alignment and the wide fan-out gives us just a worst case of 1.26 times larger than the uncompressed data. So to traverse this data structure, we begin with the same step as standard opacity micromaps. We get our hit point and convert its barycentric coordinates to a micromap index. If you take this green dot here, it's defined by the barycentric coordinates 0.19, 0.19, 0.62. If we put it into a simple branchless function with a subdivision level of 2, it'll give us out the index of 13. Once we have a micromap index, each nibble of this index gives us a child index to traverse. So if we want to sample the subtriangle 24,095, we're going to want to go to child 5, then child 14, then child 1, and finally the leaf value at child 15 to give us the value. Let's see that in action again here with the 4 tree, because the 16 fan-out is a bit of a nightmare to visualize. Because it's a 4 fan-out instead of 16, every 2 bits gives us a child to traverse. So to find subtriangle 39, we're going to take child 2, child 1, child 3. So we go to the root node, and we go to child 2, and we follow its pointer. Then, from there, we go to child 1 and follow its pointer. Now, we go to the leaf level, and we take child 3's value, which gives us a final value of 1, which means subtriangle 39 is opaque. So, to evaluate our method, we compared against 4 different scenes. We've got the standard bistro scene and Intel sponsor with the tree, Namaqualand, which is freely available online from the people at Polyhaven, and Forest, which is a custom construction, including some of the trees from the Jungle Ruins scene. We see high compression rates across all of our scenes, the highest in Namaqualand. And we see higher compression rates at higher subdivision levels. At subdivision 7, we go from 50 megabytes to 1.4 megabytes of memory usage. And at subdivision 10, we go from 3,000 megabytes, 3 gigabytes, to 9.4 megabytes of memory usage. That's 320 times compression. We can explain the higher compression rates in Namaqualand compared to the other scene because it's got smaller triangles, and lower textile density as a result. We still see high compression rates in all of our scenes. In Bistro, at subdivision 7, we go from 9 megabytes to 1.5 megabytes of memory usage. And at subdivision 10, we go from 580 megabytes of memory usage to 16 megabytes of memory usage. In our forest scene, all of the opacity micromap data is stored in just 2.8 megabytes of memory at subdivision 10, our high subdivision level. This is barely bigger than the 2 megabytes of metadata, and we have the same amount of metadata as the standard method. In Sponza, we see a slightly worse compression rate, but still high levels of compression. But at subdivision 10, we've got 70 megabytes of memory used. So subdivision 10, subdivision 6, subdivision 7, what do these actually look like? Let's take this viewpoint in Bistro. Subdivision 10 means we have 4 to the power of 10 subtriangles for every single real triangle in our geometry. There's about 1 million subtriangles per triangle. At subdivision 4, if we highlight the errors compared to alpha masking in magenta here, we can see that it's very coarse geometry, and we couldn't use this directly for primary visibility. At subdivision 7, we still have jagged edges alongside. And at subdivision 8, we still have error along our edges, but they're a little bit smaller. At subdivision 9, the errors are now fairly small, but they're still multiple pixels wide from this viewpoint. And at subdivision 10, they're fairly small. Comparing the resolutions of micromap to textures directly is difficult, because alpha texture uses bilinear interpolation, which means that edges don't need to lie along texture seams. Here it is again. To evaluate our timings, we rendered here primary visibility at 1080p. We compare our method to a software implementation of opacity micromaps. They're both implemented inside the loop of a array query loop. Neither benefit from any fixed function hardware acceleration. We can see that our method is fairly competitive with software opacity micromaps. And if we zoom in, we can see that we've got a maximum delta time of about 0.031 milliseconds. But we are consistently that little bit slower. In Bistro, we see a bigger delta, with about 0.13 milliseconds between our methods. However, our method is consistently faster than regular alpha testing. A full comparison, including alpha testing, software opacity micromaps, hardware accelerated opacity micromaps, and our method, is available in our paper for all of the scenes and for primary rays and shadow rays. So, okay. That's okay, there's a video here, it's not playing. We have an aggregate hierarchical opacity, which we store across our tree, and we don't have a real memory cost of this since it's in bits that we would use for padding anyway. We can see here it in action on this scene. This is a dust filter at various scales overlaying the high-performance graphics logo. On the top, we have a standard high-resolution opacity micromap, and we can see that there's a lot of aliasing there if we look closely. Our method ceases traversal of our data structure when subtriangles will be smaller than a pixel, and then uses that sampled opacity value to alpha blend. We never sample any texture opacity value. And we can see on the bottom that it's reduced much of the aliasing. To evaluate our timings, we constructed a synthetic renderer which rejected every intersection to ensure that all methods were testing the same triangles. We compare our regular method, with hierarchical opacity, which ceases traversal when subtriangles are smaller than a pixel, and alpha texturing with bitmaps. Consistently, both of our methods are faster than regular alpha testing, but our method with hierarchical opacity is a little bit slower. This can be explained by the need to compute what level to cease traversal at. Let's conclude. So we've contributed a lossless compression method for high-resolution micromaps. This enables high-resolution micromaps at reasonable memory occupancy. We've got competitive traversal times to the existing method, and we store our hierarchical opacity for free in the structure, in our padding bits. This can be used similar to mipmaps to reduce aliasing. We also applied all of this to regular binary alpha textures. We got as small as 0.05 bits per pixel, but if you want to know more about that, you have to read our paper. We leave to future work a few things to improve the memory occupancy of our method. We think that a better representation for fully opaque subtrees could reduce memory occupancy further at little cost to traversal. Lossy compression, where you would edit the micromap data before we compress it, could improve the number of common subtrees that are there to merge, but it would come at a cost to visual quality. Variable length pointers, so not using 32-bit for every pointer in our tree, would improve compression rates, but might come at too high a cost to traversal. And merging subtrees after a simple transformation, we put a small prototype into this and didn't see strong benefits, but it might work if you implement it differently to us. Finally, encoding the child mask in the more significant bits of child pointers works well for SVDAGs, both improving traversal speeds and compression rates, but it uses a page table, and a 16-bit fan-out means that that page table will be rather large. Thank you for listening. I've been from the University of Leeds. I've got compression code and a GLSL sampler available on GitHub if you want to implement this yourself. Any questions?
I had one question. Have you looked into the build performance of if you were to take the uncompressed OMMs and try to do this in real time? How complex does it look like to merge?
I don't think the microphone's fully picked you up, but you're saying what's the build performance of our method compared to regular? So,
yeah.
Creating regular micromaps from alpha masks is quite a slow process. There's an NVIDIA SDK to do it, and it doesn't quite run in real time. Our compression method is much faster than the micromap method, but it isn't fast enough to run in real time. It takes a few seconds to compress a scene for our sample scenes. You might be able to speed it up a little bit, but I don't think you'd be able to do it like per frame. Good question.
Great talk. So I saw that in the construction phase, there's like a lot of indirection or like multiple trees for different textures pointing at each other.
Yes.
Are there any issues during runtime with the memory access or any sort of like memory caching problems with that type of like leaps?
Yeah, so the thing is because we've got the 16 fan out, subdivision 10 we used as our high resolution micromap. Technically, the current methods let you go up to subdivision 12. But even at subdivision 12, there's only 6 steps in the tree, so it's not too bad, especially if you compare it to sampling the UVs where you've got to sample, maybe not anymore, you've got to sample 3 positions just completely incoherently from memory. And because it compresses quite well, it should be cached well. But yeah, that's why it's slower than the current method, because you have to leap through the tree.
Great talk. Can you comment on the ratio between child pointers and the actual data? So how much of the total amount is kind of taken by the child pointers?
Yeah, so it's less than 50%, but it's not a lot less than 50%. It varies by scene. The more data you have and the more patterns you have in your data, the less leaf nodes you have. And there are deduplications at higher levels, but there's less deduplications, so you end up with quite a few pointers, yeah.
Thank you.
You mentioned it in the future work, these fully opaque subtrees. I wonder if you got an idea of how often the reuse of higher level of subtree is exactly from fully opaque or fully transparent?
Yeah, so it's quite a bit. It's it varies by scene, of course. It's not more than 50%, but it's a double-digit percentage.
Thank you, Thomas.
Thank you.
That concludes the session. Thank you.
And we have a little break now, and after that we'll have Hot 3D.
I realized that there was a time that I didn't.
I think you're because we're on time.
Okay.
So you must. I think you brought us back onto time. So.
Okay.
But I think it was good. Went well. I think you talked quickly.
Yeah.
So if you, I don't know if you timed your talk, but I'm betting it timed a little bit.
Yeah, will do. I think we'll set it up such that you can see if it actually works on here.
So I will see the slides here.
I think so in a moment.
Okay.
We'll have a look if we can fix that. You just want to see it? Yeah, he just wants to make sure that it works.
Yeah, I just want to make sure.
Give me 1 second. Somebody got to switch my stuff.
and you just want to see it on the conference line. If I change it here, yeah, it'll show. It's only not showing because I have to change it. I can see you. I have to just yeah, it will work.
Yeah.
You get to
Okay. That's fine. Thank you.
Can we turn this microphone off during the breaks? So that'll be great.
Does this work? Okay. Hey, can the all 3D speakers please come forward for an AV test for the next session? So Kai and Simon, are you guys here? Oh, there's Kai. Hey. Just want to check that everything works. I think we better find out now. Hey, good to meet you, Simon. Hey, hello. Hey, Kai. See if it works. So, just see if it works. Just a quick test, so that we don't find out. Okay, guys, so the hot 3D session will start in like 2 minutes, just so that you know. Yes, I guess to get started on time, so the first talk of this session is held by Kai Zhang, and it's about an extension to the neural shading language. to the shading slang shading language that allows you to run neural networks from the shading language. And Kai is an engineer in the slang team, and he concentrates on neural slang. So, okay, Kai, I guess you can come up and plug your stuff in.
Hey everyone, my name is Kai Zhang, and I'm working in NVIDIA for the SLAN project. Today I'm going to introduce Neural.SLAN, a standard module for inline neural networks in shaders. So before the main topic, let me briefly introduce SLAN for those less familiar with it. SLAN is the modern open source shading language. It compiles a single SLAN source and existing HLSL and GLSL code to every major GPU platforms and also the CPU target. So two of these properties matter especially for this talk. It is cross-platform by design, and automatic differentiation is built into the language. These are the foundations Neural.SLAN built on. So before we get into the Neural.SLAN, let's briefly review how graphics compute has evolved. So graphics has always been built on approximations. We approximate geometry, materials, lighting, and many other parts of the rendering process because the fully detailed version is too expensive to evaluate every frame. What changes over time is the machinery we use to express and execute those approximations. So fixed function pipelines give us the texture maps. Programmable shader enables complex BRDFs and material models. Ray tracing hardware made more explicit lighting passes feasible. So the next step is neural shading, where some of these approximations are learned. So for this talk, the key question is simple. How do we make the neural network fit naturally into the renderer? So let's start with a very simplified rendering pipeline. One common place to use neural compute is in the image space processing. So DLSS is a very good example. The neural network sits at the end of the pipeline, taking images and producing images. So this that gives it a relatively clean integration boundary. So the middle of the renderer can stay mostly classic, while the neural part consumes the image-like inputs and produces the image-like outputs. The harder case begins when neural computation becomes part of the earlier rendering stages. So at that point, neural computation is no longer a separate image filter. It has to live inside the same shader execution path as the handwritten code around it. The overall pipeline can still look familiar, but some of the logic inside the stage is learned rather than hand designed. So a natural question is, what kind of workload does this introduce? So consider what happens when the shader evaluates a neural network. To represent a texture, material, geometry, or light transport approximation. So the network itself is typically tiny, just a few layers of matrix vector multiply, each followed by an element-wise activation. But the evaluation is requested from the deep inside shader execution. The inputs are shader local variables. For example, the UV coordinate, a normal vector, ray direction, or ray hit position. They all live in the on-chip memory, as does the output. Moreover, the same tiny network is shared and evaluated by every shader invocation. So that is by every thread, actually, under the GPU's SIMT execution model. So given this workload, the most straightforward solution might seem to be using an existing machine learning framework, which is very good at exactly this kind of job. So let's examine that idea. A typical machine learning workload is shown on the left. So thousands or even millions of samples are gathered into batches. And the batches are fed through the kernels whose only job is to evaluate one large network model. Well, neural shading, as we just saw, is opposite. So millions of parallel tiny executions inside the renderer that already owns the GPU. So the same mathematics in a completely different shape. So could we still reshape our workload to fit this framework? Well, it's possible, but the cost is substantial because the conversion runs in both directions, and every step of it is pure overhead. We would have to split the shader execution flow into two, and then spill the input to the off-chip GPU memory to assemble the batches, synchronize the pipeline, launch a separate kernel to evaluate the model, synchronize again, and finally load the result back from the GPU to the registers. And this entire sequence repeats at every neural network evaluation. So for a tiny network, the plumbing itself costs far more than computation it delivers. So this is simply the wrong shape for the problem. The model we want is much simpler, right? Neural code should feel like a shader intrinsic, like the texture fetch. It should consume the data already available in a shader, execute as part of the draw or dispatch, and compile through the same shader compiler. The programming model should not force user to cross into the separate machine learning system, just to use a small neural network component. So in order to achieve that goal, it will need a few reusable pieces. It needs feature encoding, because the raw shader inputs are usually not the right representation for a compact network. It also needs neural evaluation, layers, activations, and the network structure expressed naturally in shader code. For many graphics uses, inference alone is not enough. We may also want training. So differential ability has to be part of the model. And because we are targeting real-time graphics, the code still has to fit within the frame budget. So if we took all those needs literally and write them directly in shader code, we will end up with something like this. The details are not the focus here. The main takeaway is the scale of the code. So this is only the excerpt, and the real implementation can quickly grow to several hundred lines of code once the missing pieces are added. A larger part of the implementation is the low-level machinery, buffer layout, gradient accumulation, reductions, and tuning the network to run efficiently on different hardwares. So those details matters, but they are not where graphics developers usually want to spend their design effort. Their attention is better spent on the neural architecture, the content being fitted, and how the neural component fits into the renderer. The pain is not one hard line of the code. It is having to own all those low-level detail around making the neural code trainable and efficient. So can we abstract this away while keeping the neural operation inside the shader? So this is a motivation of neural.slan. So neural.slan is a SLAM module for writing neural shaders directly inside the shader programs. The goal is to keep the neural operation in line instead of moving it to a separate machine learning runtime while making the repeated low-level work reusable. The table gives the main pieces of the abstraction. The shader author works with the interfaces for encoding, neural layers, differentiation, storage, and vector data instead of rebuilding all those machinery by hand. And because of these are slant abstraction, the same source stays in renderer's compilation pipeline and can run across different hardware and graphics backends. So let's take a closer look at each abstraction. Think of this as a typical inline neural network inside the shader. The shader input goes into an encoder. The encoder produces a feature vector. The feature vector feeds an MLP, and the MLP output becomes a shader value. The interfaces mark the main parts of the structure so the user can swap or specialize pieces while still writing one shader level neural function. The first boundary is I-encoder. This is the piece that maps shader inputs into a feature space. In a texture or reconstruction problem, for example, the input might be a 2D or 3D coordinate, but the network wants the richer feature representation before the MLP. The next boundary is the IA layer. So in this example, the layer is the feed-forward layer with an activation. This is the unit that shader author normally wants to compose. Take an input vector, apply some learnable computation, apply the non-linearity, and produce the next vector. The encoder and the layers both need parameters. So the I storage is the abstraction for accessing those parameters and their layout. This lets neural.slang separate the mathematical layer from the physical question of where the weights live in, how they are addressed, and how they are arranged for a target. The separation becomes especially important when we talk about the accelerated layouts later. I vector is the representation of the values flowing between layers. At the first glance, that sounds like a small detail, but it is actually one of the main hooks for performance. A vector can be represented as simple thread local values, or it can be represented in a form that takes advantages of hardware acceleration, when such hardware is available. So the vector type is how the same layer API can select different execution paths. I will come back to this performance path later. So finally, the whole neural function can be differentiable. So the user writes the forward shader function, and the slang automatic differentiation gives us a backward path. Conceptually, gradients flow from the output back through the MLP and the encoder, and back towards the input and the parameters. Here is the current implementation status of neural.slang. So for input encoding, the interface is I-encoder, and one current implementation is permuto encoder. For layers and activation, the main interface are I-layer and I-activation. FF layer is the dense layer implementation, and the module includes some common activations. So for vector execution, the two important implementations here are inline vector and rectangular vector. Inline vector is the straightforward portable path. Rectangular vector is the hardware accelerated path. For parameter storage, the module provides band-length address and a pointer address. And for the data layout, it supports linear layout and optimal layout. So a note on the platform support is that because it is a joint condition of the types you pick, rectangular vector is available on Vulkan, CUDA, and Metal, while an inline vector runs on every target. On top of that, one constraint applies across the board. Since the parameter storage is bandwidth only, so the web GPU, since the web GPU has no bandwidth support, web GPU is the one slang target that neural.slang cannot serve today. So here is the programming model. This example defines a small neural texture function. It encodes a 2D coordinate as a feature vector of length 16. Then passes it through a 3-layer MLP with layer sizes 128, 128, and 3. So the model is defined directly in SLAM. Type aliases choose the encoder and the layers, and the eval texture runs them. The whole model is only 17 non-blank lines. The shader also focuses on the model structure when neural.slan handles the repetitive and target-specific details. So far, the API reduces authoring cost, but for graphics, convenience itself is not good enough. So the next question is whether the generated path can still run at real-time speed. So next, we will focus on the efficient execution. So let's revisit the layer operation. So each GPU thread takes an input vector, multiplies it by the weight matrix, adds the bias, and applies the activation to produce an output vector. In other words, each thread is performing the matrix vector multiply. So in the modern GPU, they provide a specialized hardware for matrix operations. It really execute matrix multiply accumulate operations, or we can call it MMA, with a group of threads working together. So let's return to the per thread view. Each thread performs a matrix vector multiply using the same weight matrix, but a different input vector. So together, this is a batch of independent matrix vector multiply. So if we pack the input vectors across a subgroup, then they form a matrix, right? So this converts the batch of the matrix vector multiply into a matrix multiply, which is exactly the shape that the matrix hardware expects. So on NVIDIA's cooperative vector Vulkan extension, or D3D's linear algebra matrix path, gave a shader-facing matrix vector API that has much of the detail. The extension handles the mapping from the per-thread matrix vector operations to matrix hardware behind the API boundary. This is a good abstraction when the path exists. It lets the shader source ask for a layer-like operation and still reach the matrix hardware. But it exists only on that specific path, and neural.slan needs to target more platforms, right? So we need a deliberate choice to prioritize the platforms that have no such extension, and build the capability ourselves first. So adding the cooperative vector backend for the targets that do support it is in our roadmap. It is coming soon. That brings us to everywhere else, CUDA, Metal, and the Vulkan and the D3D paths without that extension. So all of which still need the same packed subgroup MAT-VEC idea. So for this, neural.slan provides its own portable emulation of the cooperative vector idea. The shader level layer source stays the same. A backend specific code handles the packing, tailing, and the matrix instructions. This is where the abstraction boundary matters. User write the layer code once, and the implementation chooses how to map it to the target. This comes back to the vector tab. In the FF layer, V supplies the MAT-VEC implementation used by the eval. If V is the rectangular vector, the layer takes the accelerated path. If V is the inline vector, the layer takes the ordinary portable path. Simply, it's just a for loop. The path is useful when MMA hardware is unavailable. The layer API stays fixed. Let's take a look at how the rectangular vector is implemented internally. So each matrix hardware instruction works on a very small fixed size block. So a larger matrix multiplication must be divided into tails. Each output tail is computed by going through the matching tail pairs and accumulating their results. So for the first step, we load the W tail and one packed input tail into the MMA hardware. The result is the first first a partial product in accumulator for the output for this output tail. The important thing to watch is that we are not producing the final output yet. We are accumulating the partial products for the selected output tail. Then just repeat. Once all the tail pairs are produced, the accumulator contains the final output tail. The other key point is the layout. So different targets expect different physical layout for their best performance. So take CUDA as one concrete example. On the left, weights might start in a normal row major matrix, right? But for MMA, we first arrange the matrix as a contiguous tile trunks. So each one is actually a tail of the matrix. And then inside one CUDA MMA tail, values are assigned to the specific thread and the registers according to the instruction layout, such as CUDA's PDX MMA.M16NAKA shape shown here. The details differ by target. So the CUDA, Metal, and the Vulkan passes and other hardware APIs do not all want the same physical layout. So the neural.slan needs the layout abstraction to preserve the shader API while still fitting each target in the form it wants. Fortunately, neural.slan handles this too. It provides a utility that converts the parameters into the optimal layout for each target. So one constraint for current implementation is that whip-tangled vector cannot be used inside divergent control flow. Because the packed subgroup matrix vector needs every thread of the subgroup to participate. So if some threads have gone inactive in a divergent branch, SLAN has no way to bring them back. Only the driver has that control. So evaluation must sit in a uniform control flow. If an application does require divergent around the neural evaluation, collaborative vector remains the right tool where the platform supports it. The extension handles the divergent invocation below the API at the driver level. As mentioned earlier, collaborative vector backend for neural.slan is on the roadmap and coming soon. And once it lines, divergent code gets a first-class pass as well. So far, I have mostly described the forward evaluation, but training adds more matrix work. So this slide shows the backward formula for the forward pass. The key point is that the full backward is also an MMA problem. So we can also map the operations to the matrix hardware. But yeah, I'm not going to that details today. Putting that together, the developer still writes one layer called FFA layer v.eval with v set to whip-tangled vector. Behind the same layer call, a neural.slan handles the target-specific execution details. The vector tab selects the execution path without changing the layer API. Now, let's look at the performance. So for this class of small neural networks, it is well established that the fully fused MLPs are faster than the general purpose machine learning frameworks. So this figure compares a fully fused MLP implementation with a hand-optimized CUDA kernel against TensorFlow. So in this figure, y-axis is the throughput, and the x-axis is the batch size. The solid line measures an MLP with 64 neurons per layer. The dashed line measures one with 128. So in both training and inference, the fully fused CUDA implementation stays well above TensorFlow across the entire range. So the right baseline for neural.slan is a fully fused MLP, not a general purpose machine learning framework. So now we directly compare neural.slang with a fully fused MLP baseline. The ratio is for one layer full backward across different batch sets. A ratio near 1 means parity. The result shows that neural.slang stay close to the hand-optimized CUDA implementation while providing a shader native programming model. Here is an example of neural.slang in practice. So this is a path tracer with the neural material. The shading codes evaluates the neural material in line for every heat samples through the same interfaces presented in the talk. So to summarize, neural.slang provides a high-level abstractions that makes the small neural networks practical as shading building blocks. The same model integrates into existing shader pipeline and runs across targets, using either portable for-loop implementation or hardware-accelerated matrix operations. So this let developers focus on the neural graphics feature itself rather than rebuilding the supporting infrastructure for each renderer. So today, I only showed how neural.slang makes neural network practical inside shaders, rather than talking about the foundations of the neural rendering. If you want a deeper understanding of the neural shading and its hardware acceleration, we have a SIGGRAPH course that covers those topics in very deeper detail. Please scan the QR code to look at the course schedule. The other link takes you to the neural.slang sample code, so you can try the module yourself. Thank you.
Okay, questions, guys?
Thank you. Great talk. I have one question. A lot of the speed up you get for inference is usually achieved by quantization-aware training or post-training quantization. Is this supported with neural.slang? And the second question is, there are many formats like NVFP4 that also greatly increase inference speed. So my question is this supported by neural.slang? And if not, what would be the fallback solution if an accelerated format is not supported by the hardware?
Sorry, can someone can you repeat the question, because some words I cannot hear.
Sure. So my question is on quantization-aware training, if that is supported, and if
okay. So quantization, it's not supported by the current implementation, but since the vector type, let me change to previous slides. So here, sorry, you cannot see the slides. So the vector type takes an parameter, right? The float is the current float and half is the current element type, right? But there's no way to blocking us to implement like a 8-bit quantization type, right? So we are able to support that in the future. So the reason that is not our first priority is that in current existing like neural material or neural texture, right? So it's more common to use half type to do that, right? Quantization is more useful in a larger model, right? For example, like the language model, right? But it's definitely be possible to support that type. Actually, like the 8-bit or 4-bit type is already supported in Slang, right? So to add that support, we just need to change that parameter, the element type parameter, and make a little bit of tuning in the backend. Yeah, that should not be a problem.
Thank you. Great.
Sorry, I think you have another question about the layout.
it was a related question. So,
okay.
Yeah, the question would be if some data type is not supported by hardware, if there is a fallback layer that would emulate that, maybe in the store path. Like, yeah, FP4 is not supported in hardware by all the tensor accelerators. So, what is the fallback layer if that's not supported to ensure correctness of the execution?
So sorry, I still cannot hear clearly.
I think let's move on to the next question.
Wow, that's noisy. It sounds like this only works on the CUDA. Is that correct?
No. So for the accelerated path, so for this path, the rectangular vector, so it works on CUDA, Vulkan, and Metal. And for the inline vector, since it doesn't need hardware, right? It doesn't need hardware acceleration. So it can work on all the platforms, including the C++. But it can also support on web GPU.
No, I'm discussing graphics versus CUDA, compute versus graphics here. If you're running a pixel shader in the graphics pipeline,
yeah,
this is not supported. It's only under a compute graphics pipeline.
No, it can support on the graphics pipeline.
Okay.
So you can still use this in like ray tracing. You see the example here, right? I show the path tracer here. So you can still use this on vertex shader, fragment shader, and the ray tracing stuff.
Okay, guys, I think we need to move on to the next talk. If you have more questions, find Kai later on and talk to him.
Thank you.
So next speaker is Simon Cooks. Simon's talk is about profiling on Android. And Simon is a DevRel engineer within Google, and he works in the team that leadership team that defines their profiler.
Working. There we go. Yeah, for some reason. Okay, give me 1 second. There we go. So hi, I'm Simon Cook. I'm a senior DevRel engineer in Google's Games DevRel organization. I'm also part of the leadership team for our Android Performance Analyzer Profiler. Before that, I was in the Xbox Advanced Technology Group for about a decade, working on R&D, tech, and optimization for Xbox games. And I've been around the games industry for a tour of duty or two as well. So, what is Android Performance Analyzer? It's a new Vulkan profiler for games and high-performance graphics for the entire Android ecosystem, targeting devices running Android 12 or later. We've been collaborating with Samsung's SARC team for a few years now, and you'll hear more about their profiler, Sokotoa, in Chris Steinberg's session on Sunday at 9 a.m. Both of our profilers are built on top of a common backend, and they rely on graphics reconstruct to do the heavy lifting of recording and playback of graphics, which we'll get into shortly. Our system profiler is available embedded in Android Studio now and also as a standalone app, APA. And I'll put a QR code up at the end of the talk so you can download it and play with it if you'd like. So, profiling is difficult on Android. And most of the difficulty comes from the fact that there's thousands of different variations of devices out there with different capabilities, driver versions, shader compiler versions, and even how to handle new and secretive features like ray tracing. One thing that's important to remember is that we're not trying to replace any of the OEM and IHV tools. Those are built by experts on those teams, and they're really good at it. What we're trying to do is we're trying to service the entire Android ecosystem and act as the first tool that you reach for in your toolbox. Now, another reason why profiling is hard on Android is that we've got a lot of variance from run to run, even on what should be a nearly identical workload. So some developers report variances anywhere from 3 to 10 milliseconds from run to run. And on consoles, they see at most a couple of hundred microseconds variation. So that's a huge difference. But why? So partly it's because phones are passively cooled, and that means that they overheat very easily. When they overheat, they're throttled, and when they're throttled, the clocks are reduced until the device cools down a bit. Paradoxically, this can actually improve reproducibility because the clocks don't have as much opportunity to move around, so you get a much better result. And they stay at one level longer. Now, the other thing, though, is that mobile devices also try very aggressively to reduce their clock rates to idle levels when the GPU isn't being used to reduce power consumption, which is great for battery life, but it's not great for profiling. And the Android OS itself is pretty noisy with a lot of background tasks, the system and so on, causing big perturbations. We're actually looking into what we can do to improve that. Now, you're probably familiar with the different kinds of profiling you can do, but just in case, let's quickly review. So system traces or timing captures use event-based tracing. That is, each thing that happens records the state of a system-wide timestamp, and that info with some metadata gets serialized out in some form. With that, you can reconstruct what happened on the CPU and on the right hardware, the GPU and other SoC components, and when. Now, there's two kinds of event-based tracing. One of them is edge-triggered, which happens automatically on a scheduling boundary, and sampling profiling, which samples the system on a periodic timer. The super intrusive version of edge-triggered is instrumented, either by the compiler, by function hooking using a library like detours, or by manually adding your own scoped trace event markers. That can be really expensive to record if you're going into extreme detail, but some hardware will give you all of the detail you could ever possibly want, so much so that you'll saturate I/O bandwidth if you try to record it. Anyway, so that's an expensive one. Periodic sampling, on the other hand, is more controllable and predictable, and you can control the overhead by changing the sampling frequency. That's great if you pick a low frequency, but if you pick a frequency that's too high, again, you'll spend all of your time dumping data out to storage or out over USB or Wi-Fi. And if you pick a frequency that's too low, you'll find it hard to correlate this against your work because the boundaries when you sample won't line up with the work itself. Here's another problem. We do a lot of work with games, and games are massively real-time. And they are also very, very interactive. So it's always capturing data all the time. Games are massively real-time, and they're interactive simulations that have to regenerate their output every 8.3 milliseconds in some cases. This is great if you're automatically replaying the same work over and over again, but as humans, we tend to have a sensory fusion window that means once you get about 250 milliseconds out in terms of lag, things fall apart, and we find it really, really difficult to deal with that. So if you slow a game down, and most games require reaction times shorter than that, then you can't play it, which means you can't get it to the point where people are actually going to expose the stuff that you really want to profile. So what we need is a mechanism that's relatively low overhead when you're trying to get to the part of the game to profile. And we don't care about the overhead of recording a single frame so much because games tend to be resilient to slow frames. So this is where a capture and replay system comes in, which is the other kind of profiling. So enter LunaG's Graphics Reconstruct. This is an industry standard solution for frame capture and playback built by LunaG. Brad Grantham of LunaG is in the audience today, and he's giving a talk on graphics reconstruct at SIGGRAPH next week. Simplified, graphics reconstruct has a couple of primary functions. One is keeping track of the assets that you use while running until you decide to capture a frame, and then recording the API calls that occur and the resource changes once you start capturing. So how does this work? First, we take a capture, and then we play it back on the device. In Android Performance Analyzer, we actually keep all of the results of this because we can't guarantee that another dev you share your captures with will have the exact same phone and the exact same driver build that you have. So we want to try to make it easy so you can share these around and compare traces. And there's a special playback app that loads all of this data and plays back the API calls to do the measurement piece. It's not identical to what the game did, but in this case, it doesn't really have to be. Now, there's a cost here. It's still higher overhead than periodic sampling. And recording while a frame renders perturbs things more than anybody would like. But luckily, games are actually nicely resilient to a little perturbation. Ends up that today, the majority of game engines have matured to the point where they exploit multiple CPU cores to do all of their work. They have at least 2 primary threads, a game thread and a render thread, and they'll use other cores with task parallelism to go really broad when they have work that can be scheduled everywhere. But there's really 2 main ones coordinating the activity of the game. This allows the games to be more permissive about longer than expected frame times. The render thread can go slow, but as long as the gameplay and simulation threads keep up, the game won't fall over and get into a bad state, which is great because often games have little areas where they run really slow anyway, and it's really hard to tease all of them out. Most games aren't designed to handle very many slow frames. You can't be slow for a few minutes. And they're very hard to play in that state. And measuring timings accurately while this is all going on really isn't going to give you that much useful data other than ordering information. But luckily, we don't need to actually get all of that information. We just need to grab a capture, and we'll do all of our measurements on the replay. So there's usually 2 camps when it comes to profiling. There's the hardcore, I want everything to use bedrock real-world timing down to the nanosecond, as if I'm using an oscilloscope to look at this, or a cycle-accurate simulation. And the I don't care as long as my code runs faster when I'm done camp. And this is really the camp that we're targeting with this. There's a third camp as well, which is I need to debug this thing. And capture and replay actually helps with that process too, because there's a lot of similarities between frame profiling with a capture and frame debugging with a capture. But that's a topic for another talk entirely. Now, frame profiling is in the I don't care as much as long as I can say if my coder is faster or slower camp. It doesn't work even remotely similar to a trace mechanism, and some people balk at this, but it's valuable as long as you're willing to give up the accurate timestamp information and just look at how much things cost compared to another run. Now, this isn't new. So one more point. If you have experience with games consoles, you might be nodding along or at this point nodding off, because this has been the case for games consoles for about 2 decades. This is how tools like Pix do it. So most importantly, this is battle tested. Like, people have been using this to optimize their graphics for a long time now. Now, what are the limitations of a replay system? GPU and memory contention behave very differently because you're not running the actual game and you're not doing all of the game simulation work. You're literally just spooling out a whole bunch of metafile data. You don't get the same cache coherency effects for the same reason. The thermal load is very different because the work is different, which means that clocks can vary even more. And to measure the durations of certain pieces of work on the GPU, because we don't have driver-level control, we have to serialize some kinds of work. And many GPUs are designed to parallelize their work as much as possible, which means that you can blow out the amount of time it takes for something to run. But it does allow us to measure things, which is good. So with this, what you can do is you can play back your recording as many times as you like, super quick, thousands of times if you want. And this gives us some really, really cool opportunities. So we have a problem with profiling on Android where system activity can interfere with the results, and there's a lot of variation that I mentioned earlier. Well, the oldest trick for any kind of profiling or benchmarking is you don't measure it once, you measure it thousands of times. So we can do that, and we can use it to build up a more statistically accurate picture. We do it 100 times, and we also do it off screen to make sure it runs as fast as possible. The other problem we've got is that the GPU clocks can go idle, and then it takes some time for the GPU clocks to spin back up again. So our solution here is to trick the GPU scheduler into thinking that the GPU is really, really busy and unlikely to go idle anytime soon. And we do this with a small compute job that we run immediately before every frame. This ensures that the clocks are running at full speed before they run. Even better, this doesn't require any special OEM builds of the OS to enable. We're also looking at adding a fixed performance mode to the OS that will allow us to force a fixed clock rate with idling disabled that's within the thermal design point of the device, so you shouldn't be able to overheat and then slow the clocks down even more. This is different to the current fixed performance mode that we ship today, which has the clock set to max and has usability issues as a result because the device starts to melt. So we're going to get around that. Now, the first few frames can also be inaccurate. This is also a very common thing that you'll see when benchmarking anything. So we have an amazingly scientific and technical solution to this, and we just ignore them and drop them out of our results. So the results, well, we've tested this with a variety of GPUs on a variety of Android phones, Android XR, the new Google books that are coming out. In some cases, we've seen variance drop from several milliseconds to about 5 microseconds, which is close to the hardware clock resolution of a microsecond, which is pretty good. We're not entirely there yet, but there's more work to be done here. Now, so far I've made this sound a little easier than it actually is to do. There's a lot of technical details that come into this. So first of all, if you want to do any kind of frame looping that doesn't require you to start again from scratch every single time you do a loop, which is very expensive, then you need to be able to quickly return to the state you found at the start of each loop. Some of that is because buffers get used and written to which are needed as inputs, and so we need to restore their state. Some work straddles the boundary of the loop, and you need to deal with that. And of course, some render targets need to go back to what they were before you started rendering. And it needs to be fast, because you're doing this hundreds of times. So the full process, when we perform a frame capture, well, a frame profile, looks something like this. So first, we run a calibration pass to get a representative idea of how fast a GPU can perform a task when running flat out. Then we warm up and play back the entire frame to measure the GPU frame duration, and we loop that 100 times, discard a few frames, discard any frames where the OS might have been doing other work that touches the GPU and gets in the way, or interrupts what the playback app is doing on the CPU. Then we we measure the counters which quantify the amount of work is done, but not the duration of the work. So there's not a timestamp here. For that, we don't need to warm up the GPU because we're just caring about how many vertices did we process, how many different elements went through the GPU, and we just want to measure that so we can present that in the results of the capture. And for this, the variations are much less, although we still need to get rid of any frames where the GPU is interfered with because it's going to share the same counters, and we're still polling the counters. Currently, we loop about 20 times when we do this. We also insert idle time before and after each frame because this is periodic counter sampling to do the measurement. So we need to make sure that we are measuring from an idle point to after an idle point when we're doing the work. And of course, we have to aggregate the data using the right mechanism for the specific counter, which could either be averaging or taking the sum. Now, next, we measure each of the render pass and compute and copy durations for the different workloads. For these, we warm up, then we measure the workload duration, and we loop 100 times. The difference here is that we inject barriers to force the work to be sequential, and again, we filter out any bad samples. And finally, we take a screenshot of the output so that we can display it on the timeline so you know what was being rendered when it happens. Now, the cool thing is, this is all being productized. So there's some good news. Ole Kuznetsov worked on a lot of this with LunaG to productize this work so that everybody who uses graphics reconstruct can benefit from the same kind of functionality in the future. And LunaG made lots of additional improvements to frame looping as well, and there's more to come. I'm not going to dwell on them too much here, though, because I think this talk is going to run slightly over. I'm not sure. Anyway, so in the future, once you have this kind of functionality, you can do all kinds of interesting things and take all kinds of interesting measurements. So you might be wondering what you can do. You can, if you're on a device that, say, has a set of GPU counters you can read, but it's not the full set that you can measure at any one time, you can now multiplex the counters that you're reading, and that allows you to build up a complete picture of all of the different behavior on the GPU instead of just a small subset that would be difficult to analyze otherwise. You can also perform things like cost analysis. For example, if you modify the size of your render targets and render the entire frame twice, then if you compare the normal render target size to the 1x1 pixel render size cost, now you have an estimate for how much the pixel fill rate affected the cost of rendering your entire frame. Doesn't work for every kind of workload, but it works pretty good for traditional graphics rendering. If you can modify the capture, you can now also perform what-if analysis, and this is where things start to get really exciting, because you can substitute different things into that capture and do things like experiment with shader code changes without having to completely rebuild your app or rebuild all of the content. Frame Debugger is another similar one, and it overlaps considerably. So once you have one, you can utilize a lot of the same infrastructure as the other. And of course, if you have a good playback mechanism, you can partially run the playback over and over again to build up pixel history, so you know exactly where each pixel is being changed and by what code. And finally, if you're feeling really daring, you could do source-level line shader analysis when you don't have access to any of the actual assembly language for the source of your shader, which happens a lot on mobile, because it's all SPURV is about the level you usually get access to unless you've got IHV level tools and an NDA. But what you could do is you could truncate off the end of your shader and just run over and over again, working backwards, trimming more and more off so that you can get a full picture of the cost of each shader line. We've not done this yet. We're looking at doing it. In conclusion, we think that we've come up with a great solution that works well for a broad number of GPUs in the Android ecosystem, even those without high-fidelity trace capabilities. And given that there are thousands of devices out there, and a lot of them are at the low end, this is really, really useful. These benefits will also accrue back to the Vulkan developer community and other tool developers who are using graphics reconstruct. And lastly, just a general comment, really. Even if you don't have all of the tools and tricks you need, if there's a will, there's often a way. Anyway, thank you very much. Please grab a picture of the QR code if you'd like to find out more and get access to the beta.
Questions, guys?
So the tool that I've usually used to debug Android in the past is RenderDoc. How would you compare Android Performance Analyzer to RenderDoc in terms of capabilities and accuracy?
So I heard the first part of that, but not the end. I think what you said was you usually use RenderDoc for your analysis. How does this compare to RenderDoc's functionality?
Yeah, in terms of capability and accuracy.
In terms of capability and accuracy, I haven't personally done any comparisons. So the big thing to remember is that RenderDoc, of course, is more on the debugging side of the house. And debugging is something that we're planning on tackling in the future. But for right now, our plan is that you'll be able to export our captures and bring them into RenderDoc so that you'll be able to do some analysis there. But in terms of frame capture, we think that we have, and frame profiling, we think we've got a really good solution there. It depends on your GPU. In some cases, you'll want to have a look at the OEM tools and try them out. And you might find that they work better for you. But like, this is an ongoing development process, so we're hoping to improve radically over time.
So I've got a couple of questions. The first one is, are you planning to apply the same methodology for profiling the individual workloads in a frame?
Sorry, you said, are you planning on using the same?
Planning to use the same benchmarking approach for like the individual render passes or compute dispatches within the frame. And the second question is, what entry points are you giving the different vendors to plug their, hardware-specific counters and stuff?
I'm finding it really, really hard to hit what you're saying, unfortunately.
I can't repeat the questions. Oh, there we go. So the first question is, are you planning to benchmark in a similar way the individual workloads in a frame?
Yes. Yes.
And the second one is, what entry points are you providing for the different vendors to plug the vendor-specific hardware counters or other data?
So all of the hardware counters currently are automatically exposed as part of the Android driver since Android 12. So we've been working with them for a few years now, originally with the Android graphics inspector and now with this project. And we are actively collaborating with a lot of the different hardware vendors to come up with a plugin model. We're a little ways out from doing that because we want to get the basics first, but it's coming.
Thank you.
Thank you for your talk. With respect to filtering out sort of non-representative frames or otherwise flawed frames, is that a manual process, or is there some heuristic that you're using to determine that something should not be included, I guess?
So it's a heuristic. I think that what we're actually doing is, and I'm guessing partly because I didn't actually do the implementation here, I think that what we're looking at is the GPU activity during that time period. And if it comes from a different process, then we discard it. But that is really just pulling it out of thin air. So, but it's not a manual process. We do it heuristically.
Thank you.
Okay, then I guess we can have lunch.
Sweet.
Thanks, Simon.
Okay, can you hear me now? Okay, good. All right. I'd like to welcome everyone back from lunch. I hope it was delicious. I'm Joseph Spute. I'm the sponsorship chair. And the first thing we have after lunch is the sponsor session, which is given to sponsors who support us at the highest level, the benefactor level. We had one sponsor who did that this year, which is NVIDIA, which happens to be my employer. So I'm going to now introduce the representative from NVIDIA to share a message that NVIDIA would like you to all hear. And that person is going to be me. All right. Can we get the slide up on the projector? Let's see. I think I'm presenting. Here we go. Cool. So I have some notes that I'm going to share with you. So NVIDIA has a bunch of papers at HPG. We're very proud of them. And in addition, we're going to have a whole bunch of content at SIGGRAPH. And the marketing folks from NVIDIA would like you to know about a few things in particular. First of all is the special address, this keynote. There's going to be a lot of really cool stuff shown off there. So I recommend everybody go attend that. Then for Educators Day, attendees gain a practical understanding of how AI is being applied in education. During the Physical AI Day, there are sessions that will educate and empower developers and researchers to accelerate physical AI development with neural and classical simulation technologies, including OpenUSD, Omniverse, Cosmos, OmniDreams, IsaacSim, and Newton, and why world models and graphics are needed for physical AI. Then RTX Rendering Day, that's a full day of customer and partner sessions showcasing breakthroughs and real-world applications in real-time and production rendering. Then there's the AI and Production Day sessions, which showcase real-world work that artists and production teams are achieving with AI. You might sense a theme here. And then NVIDIA is also hosting a Build-A-Claw event daily during SIGGRAPH to promote attendees with hands-on opportunities to discover and conversations with experts to understand how autonomous AI agents can assist in their workflows as animations, visual effects, film, and media. And then you can learn more about these things at nvidia.com/SIGGRAPH. And I think I've kept this under the 5 minutes that we had for the sponsor session, so let's all thank NVIDIA for sponsoring.
Okay, hey, I'm Carsten. I'm sharing the session on real-time ray tracing and denoising. We have 3 great papers coming up. The first paper is called Real-Time Path Tracing of Massive Dynamic Foliage. It's by Ditke van Antwerpen, Pascal Goutron, Ed Bidot, Christoph Kubisch, Jan Schmidt, and Martin Stich. And Ditke will give the presentation.
Yeah. Perfect. So I am Dietker, work for NVIDIA. This is not about AI, so we are going to talk about forests. I was afraid that I would have to convince you guys that this is a relevant topic, but previous sessions already took care of that. We worked on a system, end-to-end system, to ray trace massive dynamic foliage. How massive? Our target was, this is the setup that we used. We got 230 game assets from CD Projekt. We were very thankful for that. Planted them in a world of 5 by 5 kilometers, 60 million plants, and simulated them using a wind simulation so that every plant is dynamically, uniquely animated. And the goal is to do this in real time with path tracing. So why don't we just do what everybody else is doing? We've been ray tracing this kind of stuff for a decade now. Well, ray tracing has certain benefits. When you deform plans, when you use rasterization, you can do it in the vertex shader. So you can just instance your geometry, deform it in the vertex shader, and then the deformed geometry only lives temporarily on the device and then is rasterized in a streaming fashion. You don't need the entire data set all deformed at once in memory. So the total working set is dependent on your GPU size, not on the scene size or the amount of plans. Ray tracing, on the other hand, you need all the data, all the acceleration structures, everything at once in memory to be able to ray trace this stuff. And that does not scale at all if you want to do per vertex deformation. So what do? We use instancing, similar to what the paper in the previous session about animating massive geometry already talked about. Split up the plant models into tiny pieces, small enough that the rigid animation of the pieces is smooth enough for mid to far range rendering. Close up, you could still use more advanced techniques, per vertex deformation, but close up there are not that many plants. It's really the plants in the distance that's the problem. However, even with instancing, this does not scale because you need so many small pieces, so many instances that building the top level acceleration structure and fitting the acceleration structure in memory, it just doesn't fit. So we have to use level of detail. And here we were really focusing on the instance memory aspect of the problem. So we start with these plant models in full detail, split up in tiny pieces, and start grouping them together. Well, we could use ask an artist to group these things together, but we wanted it to be fully automatic. So we guide our grouping based on the animation itself to bound the error. So we use a first order model of the displacement of the geometry under the wind simulation for some nominal wind strength, and based on that we can calculate, okay, if we put these pieces together, how much of the animation is being thrown away by making this piece rigid. And then using a greedy algorithm to group geometry together, you basically get a graph that can, at any point on this graph, you have an error and a number of instances that you can get away with at this error level. And on this spectrum, we need to pick our LODs. We can't do all of them because then we want to pre-compute them beforehand, and we will discuss later how we pick exactly which ones we took. So far, I only discussed merging the geometry. The geometry is still connected in a bone skeleton that moves in the wind. So far, we're still assuming the full skeleton, but that's still a lot of compute work for animating all these skeletons. So we also simplify the skeleton structure with the geometry. So when we merge geometry pieces, we also merge the bones. We could use a similar error metric to bound the error that is introduced by merging bones, but the error becomes very conservative. And the LOD system becomes very inefficient. The cutoff distances become very far away. But what we notice is for foliage, we're not really interested in any specific pose. We're not trying to match an exact pose. We are trying to match the motion distribution of the plant. So that's exactly what we did. Instead of trying to measure the error in the specific pose, we modeled the variance of the motion under these simplifications, again using the same first order approximation for the displacement of geometry, and then we refit the rigidity constants of the skeleton to achieve a similar mean and similar variance under nominal wind strength. This worked really well. The error in the fitting is much smaller, relatively small compared to the error of just merging rigid pieces together. And you can interpolate the rigidity constant, so you also don't have any popping issues with the animation. As I said, we merged the geometry together. This has the downside that you will have to duplicate basically the geometry for every LOD, because at the reference level, you have all these small pieces, and you have one acceleration structure per piece. But as you merge them, you need one acceleration structure per merged blob of geometry. However, we can use the new cluster API that comes with DX 2.0 to share the bulk of the geometry and the acceleration structures between the different LODs. So what we do is we transform the entire tree geometry in tree space, cut it up in clusters, and now we can regroup these clusters into cluster acceleration structures at different granularities. So at the finest granularity, you basically have a cluster acceleration structure on top of maybe one or a few clusters, and on the other end, you just have one cluster acceleration structure over all the clusters, and this way you can reuse all that geometry, and you only have to have this little top level, it's not a top level acceleration structure, it's a cluster bottom level acceleration structure, but it's kind of an acceleration structure on top of these things. So this already helps a lot with keeping the LOD memory in check. However, these clusters don't have transforms. The cluster geometry needs to be in plant space. So if there's a twig in the tree that is replicated throughout the tree, like hundreds of times, and this happens quite a lot, then we would have to flatten this twig throughout the tree as well, which still blows up the amount of all of LOD memory. So we need to simplify the twig geometry that is being flattened, and for that we came up with this simplification pipeline. Starting with a twig, we first apply edge contraction, which is a pretty standard technique to simplify the mesh, but we heavily constrain it because one of the problems with edge contraction is that if you apply it to foliage, it tends to thin out the geometry because there's a lot of tiny features and they just disappear and the twig won't look the same anymore as its original. And so we constrain it to make sure that the feature size, a certain feature size is maintained. And then using that simplification, we chunk it into small volumes. And then for each volume, it's basically a bunch of triangles in a small volume. There we selectively decide, do we replace this chunk by imposters or do we use the original triangles, depending on how many triangles are in there and a heuristic for the amount of memory that each of the two choices would result in. If we replace a chunk by these imposter triangles, we bake OMMs, which were discussed in a previous session as well, to approximate the geometry by basically an opacity map on this imposter. And now we can, when we have to instance this twig throughout the tree, we can just flatten the imposter triangles, which is just a handful of triangles in the tree, while still reusing the same OMMs. So now we get kind of this instancing effect back while still being able to merge the geometry together. Here you see the OMM replacement in action. So one chunk would be replaced by three perpendicular imposter triangles with the OMs on them. Here at the bottom you see a bunch of twigs and how they could look like depending on the error level that you're aiming for when you replace them by these OM replacements. And then for every replacement, we project all the geometry on these perpendicular imposters to bake the OMMs. When we project geometry on three different parallel perpendicular planes, we usually end up increasing the amount of area in screen space. And similarly, we also increase the amount of occlusion in the model, which changes the look. So what we did is to normalize that, we basically measure how much area increase is being caused by this projection, and we correct that using partial opacity. However, as discussed before, partial opacity is expensive. You have to go back to an NEH shader, evaluate it. That's something we don't want to do. So we use a stochastic opacity. And stochastic opacity is a pretty standard technique. Instead of doing partial opacity, you just stochastically decide is it fully opaque or fully transparent. But we bake this into the OMM using a dithering pattern. So the OMM itself only has fully opaque and fully transparent micro triangles. And if a piece of the OMM had partial opacity, then using dithering, it kind of approximates this opacity. And you see here how the distribution, the screen space distribution is shifted back to its reference after applying this dithering pattern. For the shading of the OMMs, we bake the geometry fragments that were projected on the OMMs. We bake them in auxiliary shading data. So we don't bake the material model or parameters itself. We just reference the original material, and we bake the normal and the UVs, which has the advantage that we can combine different material models and bake them all into one OMM. We don't have to worry that they all have to use a uniform material model or something like that. And we super sample the OMM so that we have enough bits to do proper dithering. One thing we ran into is that when you project geometry on 3 perpendicular planes, and then you look at the projections, that the distribution of shading normals gets subtly biased. The details are in the paper, but what basically happens is that grazing angles get amplified. You see more grazing angle normals than you should have, and the face all normals get suppressed. We can't, because it's view dependent, we couldn't really fix that in the OMM, but we still wanted to have an aggregate similar brightness. So what we did is we apply a bias technique where we pull the normals that we see slightly towards the viewing direction, and the amount that the pulling is based on just fitting it with empirical data, so that we achieve the similar normal distribution. Having all these pieces in place, now we can build these LODs. Now we have to select a set of which one we want to pre-compute, and here we pre-compute by minimizing expected memory, which is both the memory for the assets themselves and the total instancing memory that we expect to need. And that is based on some target configuration. So what's the screen resolution going to be? What is the screen space error that we are willing to live with? Maybe 1-2 pixels, something like that. What's the field of view? What's the average density of this particular plant in the world? And what is the nominal wind strength? And that's what we run the offline optimization for. And then using dynamic programming, we select the optimal set of LODs. And then at runtime, we look at the actual realized configuration. And based on that, we decide what the cutoff distance needs to be for every plant and which LOD we need to pick. So if the actual wind is a bit above the nominal wind strength, it will push up the LOD to a finer detail, which allows it to adapt dynamically. If there's an explosion somewhere, that temporarily the plants in that region will have a finer detail so that the motion, which is then more extreme, doesn't look too rigid. Here are the results focusing on the memory usage. So you see at the top, if we don't use the cluster acceleration structures and we don't use the OMMs, and we just use edge contraction to simplify, you see that we need a lot of data for the lot 1 and above, way too much for this to be a feasible solution. And as we apply the clustering to reuse across LODs and the OMMs to reuse within an LOD, we get the lot memory into a reasonable amount where this becomes feasible on a modern graphics card. Some words on the LOD transition. So far we bound the geometric error in screen space because the clustering of geometry for OMM replacement, the thresholds there are geometric thresholds, and the same as for the edge contraction. But we don't bound the shading error. Like we did some tricks to make sure that the aggregate looks the same, but for one particular pixel, there's no mechanism that makes sure that this pixel, that the error is bound within some threshold. But luckily, For real-time path tracing, we need a temporal denoiser anyway. If you path trace a couple of samples per pixel, it's a noisy mess. And we found that temporal denoisers are great at smoothing over these shading, these subtle shading differences. And the error that is introduced during the lot transition is within the error margin that you have anyway, the drift from applying a denoiser from consecutive noisy frames. So we're pretty happy with the result. The final piece of the puzzle is now that we have all these instances of all these LODs, we need to build a top-level acceleration structure over these. And even though we reduced the instance count by quite a bit, building a top level over all of these instances is still very slow. And we didn't manage to reach the 60 frames per second target that we wanted to hit. But we noticed that using the error metric for the displacement in the animation, we can also find a cutoff distance where animation is no longer necessary at all, because all the motion falls within 1 or 2 pixels in size. And so when we apply this to the geometry, we can basically just stop all animation at a certain distance depending on the size of the plant. And we can exploit this by using the partition TLAS, which is also coming with DX 2.0, where we partition the whole world in partitions of roughly equal amount of instances, and then we only update instances that are actually in motion, so that partitions that have only static instances don't need any work, and this speeds up the top-level acceleration structure build by, in our case, about 6x, which made it feasible to do this in real time. And here at the bottom, you see kind of what the partitioning looks like. We use a quad tree to partition the instances in real time in the partitions, and it adapts to where the camera is on the fly. And here the rendering performance results, a breakdown of the scene. At the top, the dotted line is what the frame time was when we still used a regular top-level acceleration structure. So that was more in the range of the 30 FPS. But switching to partition TLAS, you see a huge drop, and we managed to achieve the 60 FPS real-time targets that we need for this to be useful for modern games. The code will be open source. We're still working on some replacement assets because we can't release, for obvious reasons, the assets that we got from CD Projekt. We are quite far with that, and we expect this to be ready in autumn this year. I have also a quick video of 1 minute, just so you can see the system in action. So we have a multi-light system also implemented in the application. Here you see how the LODs adapt to the local wind strength, which is caused by these hovercrafts. In the end, you can only really judge LOD popping by looking at live footage. I can show you graphs all I want, but you want to see it in a video. Most of these big trees, they have an initial transition distance of like 40, 30 meters, just to get some idea of. Okay, thank you very much. This was our presentation.
Okay, any questions?
Over there.
Hi, that was a great talk. You said you did stochastic transparency on the micromaps. Is that just on the 2-bit 4-state micromap?
Yeah, correct. We just use a 2-bit micromap, and then we basically super sample it and then bake the dithering. So the stochastic choices are baked into the OM instead of doing them during rendering.
Oh, cool. Thanks.
Okay, any more questions? Okay, I have one. So how much is the quality dependent on DLSS? So what would happen if you replaced the denoiser with, for example, SVG or something like that?
So we didn't really try it with a non-temporal denoiser, for example, and we mostly tested with DLSS, different versions of it. So I couldn't really say how it would look on another denoiser. I have to admit that. Of course, you do need a denoiser anyway because it's absolutely horrid without a denoiser. But even if it doesn't really depend on the LOD for that, it's a noisy mess either way.
Thank you. Any more questions?
So you took a lot of different approaches to optimizing the geometric representation. What was the thought process leading you to each individual optimization? Like, did you use a profiler to identify bottlenecks, or was it more like a conceptual, theoretical approach that you were using to come up with ideas for what to optimize next?
We mostly found the memory bottlenecks as we went along. So initially starting with the rigid animation approach and bounding these errors and then noticing that it's still way too much memory. And also a large part was looking at the latest APIs that came out, like how can we use these new APIs to solve this problem, which then led us to, okay, can we use OMMs? We also looked at linear swept spheres, for example, as an alternative approach. In the end, we converged on using OMMs because it's available on more graphics cards and it performed better memory-wise. But a lot of it was looking at what are the recent new tools that we have available that could make this possible because it didn't seem feasible before.
Thank you.
Okay, let's thank the speaker again. Okay, the next talk is compatibly guided neighbor selection for resteer. It's given by Orion Jenkins, and the co-authors are Markus Kettunen, Dagi Lin, and Rava Ramamuti and Chris Wyman. Okay, take it away.
Hello, I'm Orion Jenkins, and I'll be presenting our paper, Compatibility Guided Neighbor Selection for Rester. So ray and path tracing, as we all probably know, enable highly photorealistic rendering by averaging large numbers of samples, 65,000 in the case shown here. And this might be tolerable for an offline rendering context, but if we want to render scenes at interactive frame rates, we can typically only afford about 1 sample per pixel. And at a single sample, naive path tracing gives you this, not particularly impressive. Because of this, these techniques were generally considered offline only and out of reach for real-time applications. But this has been changing in the past few years, in a large part due to an algorithm called Rester. Rester improves quality by reusing lighting samples temporally and spatially. First, Rester uses samples from the previous frame to improve the quality of the current frame. If you chain this for several frames, it lets information accumulate over time, significantly improving output quality. Then Reister applies spatial reuse within the current frame, allowing pixels to benefit from the samples of their neighbors. If we go back to our one SPP path trace, applying temporal reuse brings us here, and applying spatial reuse brings us here, getting us to something that's good enough a denoiser can finish the job from there. So Reister is incredibly effective at reducing noise, but there's a hidden cost here that we need to talk about, and that's correlation. When you reuse samples between pixels, you correlate the estimates of those pixels. This can lead to clusters of duplicated samples and structured noise patterns. The render on the right shows a somewhat extreme example of the resulting correlation artifacts, which are distracting for a perceptual system, but they're particularly problematic for denoisers that expect independence between pixels. And so these correlations have made Reister challenging to integrate into production pipelines, despite the noise reductions the algorithm offers. Thus, it's essential that we both understand and minimize these correlations. And our paper and today's talk addresses both of these points with two key contributions. First, we provide a quantified characterization of the fundamental trade-off between error and correlation. We'll show how Reister reduces error, measured with symmetric mean absolute percentage error, SMAPE, on the y-axis, in exchange for increases in correlation, measured with relative spatial covariance on the x-axis. Tuning Reister's parameters, in this case the radius used for spatial reuse, trades correlation for noise, or traverses this curve, but simultaneously reducing both measures, that is, to shift this curve towards the origin, requires algorithmic improvements. Our second contribution is one such algorithmic improvement. We propose compatibility-guided neighbor selection. Rather than choosing neighbors uniformly at random, as in prior work, we perform a fast multi-tap search and select our spatial neighbors proportional to a measure of geometric compatibility. This improves the Pareto frontier of the error correlation trade-off, reducing both measures with tunable control over the balance. And of course, we do all of this in real time. So to start, let's talk about where correlation comes from in Reister and what forms it takes. And the key conceptual idea is that sample reuse exchanges variance within a pixel for covariance between pixels. First, temporal reuse lowers variance, but it exchanges it for temporal covariance. Pixels are correlated in time across frames. Spatial reuse further reduces variance, and it actually helps to break down some of this temporal covariance, but in exchange, it increases spatial covariance. Pixels are correlated with their neighbors within a frame. And we can't prevent these exchanges, but we can try to improve their efficiency. We can try to get a better exchange rate between variance and covariance. And a lot of work has focused on temporal reuse in recent years, and actually made it very robust and quite efficient with respect to this trade-off. Spatial reuse, on the other hand, has received a lot less attention, and in practical deployments, it has become a key bottleneck. So to demonstrate where it falls short, we'll take a closer look at the prior approach before improving upon it. So let's say we're trying to render the pixel shown here in red in ViChaJar. The current algorithm chooses some number of neighbors denoted M within some local radius denoted R. Any pixels with obviously dissimilar integration domains, such as the upper left point on the wall, which spans a normal discontinuity, are rejected. And any remaining neighbors, at most M, are reused from. Now, this approach works very well for simple scenarios, like our pixel here on the floor, where most of its pixel space neighborhood is likely to be geometrically similar. However, if we consider a more challenging case, such as this pixel on the table, it becomes much harder to find compatible neighbors. The majority of its local pixel space neighborhood spans some form of discontinuity. In many cases, all chosen neighbors will be rejected, and spatial reuse will be effectively disabled. So this leads to a couple of issues for pixels with geometrically discontinuous neighborhoods. First, if we look at a heat map of per pixel error in an output of Reister, we see significantly elevated error precisely where spatial reuse struggles to find compatible neighbors with the current randomized selection. Spatial reuse is failing to reduce variance in these challenging areas, despite working well on the walls and floor. In addition to elevated error, these failures also lead to persistent temporal correlations. Now, these are hard to visualize in 2D, but one tool we have in our quiver is an XT plot. And so to create these plots, we'll isolate a 64 by 1 strip of pixels in an animated sequence. And at each frame, we're going to capture this strip and stack those captures vertically. This lets us visualize temporal correlations as persistent vertical streaks. We'll study 2 strips of pixels, one from the back wall and one from the grazing angle on the table. And currently, we have only applied temporal reuse. So the temporal correlations are initially quite severe. We see frequent vertical streaks that persist for many frames in both XT plots. These vertical streaks are exactly the temporal correlation artifacts that distract our perceptual system and reduce denoiser efficacy. If we apply spatial reuse on the strip of pixels on the wall, the vertical streaks dissipate almost entirely. And this is what we want to see. However, for the strip of pixels on the table, the streaks remain clearly defined. Spatial reuse is failing to break down temporal correlations in these pixels. So spatial reuse in its current form is leaving behind pixels with geometrically discontinuous neighborhoods. But what can we do? How can we improve spatial reuse in these areas? If we go back to our algorithm, probably your natural first question is, well, why not just decrease the radius? Neighbors closer in pixel space are less likely to span a discontinuity and more likely to be compatible. And this is a good intuition. It actually does work to some extent. If we start with a large radius of 100 pixels and progressively decrease it, we see that noise does indeed decrease, but as we get to smaller and smaller radii, returns diminish, and we start to see structured noise patterns appearing. At very small radii, these patterns become increasingly obvious. We're trading reductions in noise for increases in spatial correlation artifacts. So we contribute a characterization of this perceptual trade-off by measuring relative spatial covariance. The exact details are in the paper, but we're just estimating the average covariance between a pixel and its local neighborhood, normalized by pixel luminance. If we do this and we plot it against SMAPE, it lets us understand the trade-off between the two. So each point here corresponds to a different spatial reuse radius R. At large radii, we have high variance, high noise, but spatial covariance remains low. There's no visible correlation artifacts. At small radii, we get much lower variance, but we now have high spatial covariance. And radii in between trace a smooth curve between these extremes. Prior research work has selected a radius of 30 based on perceptual tuning. This captures most of the noise reduction that's on the table with low enough spatial covariance to generally go unnoticed by our perceptual system. However, denoisers are more sensitive than our perceptual system, so in production settings, it's common to increase this radius to 50, accepting a little bit higher noise to keep those correlations at a tolerable level for today's denoisers. Now, these curves are helpful for understanding and tuning Reister, but what we really want to do is beat this curve, not just traverse it. We want to reduce both measures and shift this curve towards the origin. So how do we get here? How can we improve spatial reuse to reduce both simultaneously? Now, if we go back to the algorithm, we now know we can't just directly decrease R. But the next obvious question is, can we increase M? Can we increase our neighbor quantity to increase the likelihood of selecting at least one compatible neighbor? And unfortunately, not really. Reuse itself requires tracing rays, and so we can't typically afford M of 1 or maybe 2. But a better question is, can we increase neighbor quality? Can we keep M fixed, but make sure all M are highly compatible? And it turns out that evaluating neighbor quality is much, much cheaper than reuse itself. And this leads to our algorithm, compatibility-guided neighbor selection, or CGNS. Rather than drawing M neighbors at random directly, we draw a large number, k, of candidates. For each candidate, we compute a score function that measures its domain compatibility with our query pixel. We then sample M neighbors from these k candidates proportional to their compatibility scores. And we do this in a single pass using weighted reservoir sampling. Finally, we reuse from these M selected neighbors. Now, this algorithm is compatible with any score function you can dream up, but we propose a practical geometry-based heuristic that builds on the original binary rejection criteria from the 2020 Reister paper. This checks a threshold on normal depth normal and primary hit depth similarity for the gbuffer primary hits. We generalize this into a continuous valued score function suitable for proportional sampling. We define it as the product of a normal similarity score and a primary hit positional similarity score. And this maps directly to the two terms of the binary criteria, with the product replacing the logical AND operation. Our normal score is just the dot product of primary hit normals raised to a tunable strictness exponent. And our position score, we just use an exponential on the distance between the primary hits with another tunable scale parameter. Now, the paper includes a detailed motivation for this formulation in the context of Riester. But for now, I just want to highlight that this formulation directly follows many common denoiser edge-stopping functions. And while we're applying it in a new context, this kind of geometric similarity measure is well established in graphics literature. So with this score function in hand, let's return to our existing Riester implementation and apply CGNS. At first, you might not notice any difference. If I toggle back and forth, the walls, the floor, really most of the render look the same, but this is because the existing approach already works well for those simple cases. CGNS has little to offer. But if we zoom in on a more challenging part of the scene, the difference becomes obvious. We see clear reductions in noise along the table as well as on the teapot handle. CGNS is giving more effective reuse for these geometrically complex areas. You can also see this if we return to our XT plots from earlier, where the baseline approach failed to eliminate temporal correlations. Here, we see that CGNS does a much better job of dithering out those vertical streaks. This gives a render that is less visually correlated temporally and much easier to denoise. However, because most of this scene is geometrically simple, the quantitative improvement is small when averaged over all pixels. CGNS does indeed improve the Pareto frontier, but only slightly, by a point or two of SMAPE at most. But of course, scenes are almost never this simple. In practice, we care much more about scenes like Emerald Square, shown here, where geometric complexity is much more widespread. Here, the current approach fails much more often, and CGNS has more to offer. Now, if we toggle back and forth, you can see clear improvements in the grazing angles on the path, the tree foliage, the grass, and the fence on the right. If we zoom in on that fence, we can see a significant noise reduction. CGNS is guiding pixels on the fence to reuse from each other, pixels on the bike rack to reuse from each other, and pixels in the background to reuse from each other. And because most of the image now observes a benefit, the mean improvement is much, much larger. As in the baseline, the reuse radius can be tuned to select a desired operating point, but we consistently get a better exchange rate. CGNS gives lower error at any level of covariance. So this is clearly beneficial for overall quality, but what does it cost? And if it only benefits some pixels in some scenes, do we really want it enabled by default? Let's take a little bit of a closer look now at the runtime cost of our algorithm. So here is a per shader breakdown for Emerald Square. And running our algorithm itself increases frame time by a bit less than 1%. It makes up that small purple sliver on the bottom right. In addition, applying CGNS increases the runtime of spatial reuse itself. Now, note that we did not change how spatial reuse is performed. We just provide better inputs. In a scene like Emerald Square, the prior approach rejects many neighbors, often disabling spatial reuse altogether. We pay this previously skipped cost. And for a scene like Emerald Square, this skipped cost is the majority of our overhead, but it's still under 4% of total frame time. What this means is that on simpler scenes, where the baseline approach already works well for most pixels, there's little skipped reuse cost to be paid. In these cases, our algorithm's overhead reduces to the very small cost of the selection algorithm itself. So while the benefit of our approach is more sparse in these simple scenes, our cost is proportionally much lower. CGNS provides benefit where it can, but it costs very little where it can't. Okay, so let's look ahead to the future of CGNS in both practice and in research. So I wanted to include a brief slide on what it would take to bring this to production, but I really don't have much to say other than go implement it. It is compatible with all screen space-based Reister techniques, including DI, GI, and PT, as well as most recent advances, including area Reister and reservoir splatting. It takes a few hours to implement, and it provides significant benefit in the most challenging pixels in the most challenging scenes. And teams inside NVIDIA have already been doing exactly this. One of my co-authors, Dachi Lin, recently added CGNS to an experimental version of RTX Remix. And he was motivated by scenes like this challenging one from Portal, where many pixels are going to fail to find compatible neighbors with random selection. Applying CGNS here provides significant benefit. If we toggle back and forth, we see many previously dark pixels, both in the background as well as on the fence filling in, giving the denoiser a lot more information to work with. Looking ahead on the research side, I do want to highlight two possible improvements. First, our compatibility heuristic does not account for disocclusions or shadow edges. Improved score function may provide good results with dedicated handling of these cases. Second, we operate solely on G-buffer values, which may not always reflect the true primary hits when you are using subpixel sampling with approaches like area Reister. In these cases, denser G-buffer sampling or other ideas could be beneficial. So to wrap up with a couple of key takeaways, the key conceptual takeaway is the fundamental idea that Reister is exchanging variance within a pixel for covariance between pixels. And this happens both temporally and spatially. This covariance must be understood and minimized, especially when integrating Reister with denoisers that assume independence between pixels. What this means is that evaluation with error metrics is generally insufficient for resampling algorithms. Future work should also quantify covariance to show that no cost is being swept under the rug. A key practical takeaway is that CGNS can and probably should be added to your Reister implementation. It makes spatial reuse more robust in challenging scenes and provides a better exchange rate between variance and covariance. And it does this with an overhead cost that is proportional to the benefit provided. Crucially, the hardest pixels in the hardest scenes stand the most to gain. Our algorithm helps precisely where other approaches struggle. And with that, I conclude, and I'm open for questions.
Thanks for the great talk. I may have missed this, so apologies if I'm asking a redundant question. But when you do sort of the edge filtering, the geometry filtering sort of approach of picking neighbors, does that amount to another layer of importance sampling, or does it introduce the possibility for bias or incorrectness or inconsistency?
Great question. So long as you do not inspect the actual details of the samples, Reister remains unbiased. This was proven in the GRS paper a few years ago, and it's the existing rejection criteria that reject neighbors based on G-buffer values are exploiting this fact. So we are not actually inspecting the true primary hits. We are solely operating on G-buffer values. In the case of Reister PT with center-sampled paths, that is exactly representative of the true primary hits, but it still remains unbiased because we're sampling them independently. Once you introduce area Reister, that may not be representative, and so in that case, we are approximating the true primary hits with a G-buffer. This lets us remain unbiased, but for high-frequency detail can introduce some problems, because you might, for example, have your G-buffer sample that misses a foreground object while your true path sample hits the foreground object. So that's denser sampling could help that, or we're looking at other ways of addressing that now.
Sorry, back here. You talked about 1 ray per pixel earlier. Do you also cover things like rays per pixel variation across the image and pixels per ray variations?
I mean, do we study that explicitly? Could you clarify the question? Do we study that in particular, or?
Or is that part of this work? Pixels per ray and rays per pixel varying across the image?
So we're somewhat agnostic to which version of Reister you use. So we test on a single sample per pixel implementation of Reister PT with area Reister and reservoir splatting, but we've implemented this with Reister DI, Reister PT with different configurations, with and without area Reister. So you could use it with with different configurations of Reister that trace more rays as well.
Great talk again.
So earlier on, you showed that like scenes like Vicha's Ajar like didn't have a lot of benefit because of the flat walls. Can the algorithm skip that sampling part in order if it like knows it's going to be not as effective?
Yes, so there's one kind of caveat that's discussed more in the paper that we add here where basically there's an early termination criteria in this process where we typically are drawing 32 candidates, but if the first subset are very high quality, where we initially find several high-quality candidates, we do have an early termination check that saves runtime. It's saying, hey, everything we're drawing is compatible. I must be on a diffuse wall or a diffuse floor. I don't need to continue this search. Let's bail out of here. And so in Vicha-Jar, we're frequently terminating early because we find compatible neighbors right away. So there's a little bit of adaptivity there. Yes.
Thanks.
Thank you, great talk. So I have a question about the performance. So I noticed in the Emerald scene it was about 30 milliseconds per frame, right?
Mm-hmm.
But you tried it in Portal RTX Remix, so I assume there's a different implementation which runs much faster, I suppose.
Mm-hmm.
So if you have any performance data for that, and if you could tell us the overhead of your methods on top of the basic Portal implementation.
I don't have profiling experiments for Portal. That was an experiment that actually Dachi just sent me quite recently. So I just have those screenshots and a little bit of a perceptual report from him. But we've implemented this now onto several different implementations of Reister. And it's actually been reproduced externally already. And across all of those, we're consistently under 5% overhead is the highest we've ever seen. And that also depends a bit on the parameter configuration. You can tune the number of candidates as well as the radius to control the cache coherency and the amount of compute performed. So there's flexible knobs, but in general, we've seen under 5% overhead.
Great. Thank you very much.
So I actually really love the visualization of the temporal covariance. Are visualizations like that something that you come up with in the course of development in order to understand the problem, or did you come up with that just to like present it at the end?
This was first provided in, I think, conditional resampled importance sampling, a paper a couple of years ago. So this has been used before, these XT plots. But I think the bigger question that this gets at is that these correlations are very, very hard to study, and even harder to study in a two-dimensional research paper format. So we're kind of tackling that on two fronts. First of all, we're using visualizations like these here, where you can start to see these correlation artifacts. But then we're also proposing new metrics that do a better job of capturing these things. So the paper includes a lot more detail, but we quantify both spatial covariance, as discussed. We also quantify this temporal covariance, so applying the same metric temporally. And probably the bigger picture mental model here is that it's kind of a three-dimensional loss landscape where error is one axis, spatial correlation is another axis, and temporal correlation is a third axis. And it's really easy to squish one of those and pay an unexpected cost in another. And so the bigger point here is that you can't minimize what you can't quantify. And so instead of just tuning knobs and seeing how it perceptually changes, we're trying to provide a toolkit of measurement, like measures that can actually quantify these perceptual phenomena. And so it's not public yet, but we will have a Python pip installable package out pretty soon that lets you quantify these things from a stack of EXRs directly for both temporal and spatial correlation.
Okay, let's thank the speaker again. So the last talk in this session is optimizing Vulkan dispatch schedules for real-time unit denoising. The author is Karl Sassi, Johannes Hanniker, Lukas Alba, Rainer Dolb, and Carsten Daxbacher. Talk will be given by Karl Sassi. Okay, take it away.
Okay. Does it work? Okay, yeah. Hi, I'm Karl. I'm going to present a neural network compiler that we designed for denoising architectures. And at the start, just to give a bit of motivation, when we render images with path tracers, we, of course, always end up with this noisy mess. And one solution to get rid of this is to just you shoot more arrays. But, of course, in a real-time setting, that's not really an option. So a faster alternative is to use something like a denoiser. Closer. Does this work? Closer? Okay, no, this works. Okay,
So yeah, a faster solution is to use a denoiser. And Intel OpenImage Denoise is one such library. It's quite an industry standard now. It's a default denoiser in Blender, also available in a lot of other renderers. And if we look how it works internally, it's actually surprisingly simple. It's a UNet with direct prediction, which is applied in a uniform color space. And just to give a quick recap here what UNets are. So it's a convolutional neural network where in the encoding stages we use max pooling operations, which reduce the spatial resolution. And then in the decoding stages we use upsampling to increase the spatial resolution again. And then we have skip connections, which reintroduce detail from previous layers. And these are then just implemented as channel-wise concatenations. And of course, it's a convolutional neural network, so in between we just mix a couple of convolutions. The question that we essentially want to answer is, well, how can we integrate these neural network workflows into rendering engines? And if we look what already exists, we essentially end up with a workflow which looks similar to this, where we design and train our models in tools like PyTorch. Then we export them to Onyx, which is an exchange format for neural networks. And then, depending on the framework that we end up using, we may have an additional offline compilation step, like for example with TensorT, where we compile Onyx into some other intermediate representation. And with almost all frameworks that we look at, we end up with a runtime library, and then everything that the renderer does, it just links against this library, and then at runtime we pass a buffer, the library does the inference for us, and then we get back a buffer to the denoised output. Now this works, but we think that there's a couple of problems with this. So first of all, these DNN runtimes are very opaque, and this is a problem because oftentimes this means that they duplicate a lot of the code where we already have infrastructure for inside of renderers, like memory allocators or things like render graphs. Another problem is that oftentimes, or essentially always, these libraries essentially always execute on platform-specific backends, like CUDA or ROCm. And now we, of course, need some way to synchronize between something like a Vulkan semaphore and a CUDA semaphore. And that's definitely possible, but from an integration point of view, it just doesn't feel quite right. And there's also the fact that these runtimes can be quite large, and depending on the application that we want to ship, sometimes that's not really a cost that we want to accept. So these are all from an integration point of view, but there's actually also an argument to be made from a performance perspective. So if we look at what existing compilers give us, we end up with a dispatch schedule which looks something like this, where pooling and upsampling get materialized as separate dispatches, and at least with TensorT, concatenation gets implemented as a memory copy. And we will look at more optimized dispatch schedules later, but just so we get an intuition here, concatenation being implemented as a memory copy should be kind of a red flag, just because when we think about it, we could just have a computator which reads from this other memory address, and then we don't even need the memory copy. So there's definitely room to improve this. So to summarize, these existing neural network frameworks don't integrate too well with existing rendering engines, and even worse, for UNets at least, they also don't really give us the best performance. So what can we do about this? Well, there's one solution which will always work, which is just to write everything yourself. And this sounds like a really naive solution, but there's actually real arguments why you should do this, at least in a production setting. So if you write it yourself, you can just use your engine native memory allocator. In the best case, you can just map it to render graphs. You don't really need to worry too much about synchronization. In the best case, you can just record the denoiser into the same command buffer that you already have for path tracing or for post-processing. You don't end up with any extra dependencies because, of course, you wrote it yourself. And in the best case, this is even faster. So this seems like the obvious choice, but there's one problem with this, which is that writing these implementations is very difficult. And the reason for this is that whenever you write high-performance computators, they have to be parameterized by things like tile sizes, and choosing those tile sizes just takes a long time, at least if we have to do it manually. And if we now have to do this for 20 dispatches inside of a model, just easily takes a day. It's not a very fun thing to do. And the worst part is if we now change the model, like changing a channel count, or if we switch to a different GPU, we essentially have to do all of this work again. So this is essentially what we try to do. So for this, we wrote our own compiler, which instead of giving a runtime library, we just give you a file which contains a list of optimized computators, and then you just execute those natively in your renderer. And with this, we essentially get the best of both worlds, where we get integration quality, which is quite close to a handwritten implementation, but we can still get the performance benefits that we would expect from a compiled version. Okay, so now let's look how the compiler actually works. So as an input, similar to most other compilers, we take Onyx, and we can think of this as a computational graph. So here, edges represent logical operations, and nodes represent tensors. And there's two things that are special about this graph. So Onyx itself doesn't give us a memory layout, but for the inputs and outputs of this network, we of course need to fix it to something, because this will be the interface to our renderer. And the second part is that this graph contains operations which read two tensor values. And what this means is that we end up with edges that have more than one source node. Formally, this type of graph is then known as a hypergraph. Intuitively, this doesn't change too much, but when we later do algorithms on these data structures, some of them become quite hard to implement, but yeah, intuitively this is not too important. Okay, and then on the other side, what we would want to get as an output is just a list of SPIR-V binaries with metadata. And the metadata is things like the push constants, dispatch dimensions, what descriptors we have to bind, and how, things like buffer sizes and so on. And then to execute this, it's quite simple. You just execute all of these in sequence, and afterwards you have a denoised output in a storage buffer. Now, the obvious question is, what does the compiler actually have to do here? And first, for each tensor, we have to choose a specific physical memory layout, and we have to decide how we want to map the logical operations to something that we can execute on a GPU. And for this, we need to choose a specific computator which implements the operation. We also have to decide which of the logical operations we want to combine into a single dispatch, and we have to choose a specific parameterization of the shader, so essentially our tile sizes. And at a high level, we can think of all of these decisions as a search space. And what a neural network compiler does, it just searches the space for the fastest implementation. And in the general case, or for general purpose compilers, making these decisions is a very hard optimization problem, because, or at least making these decisions, all of these decisions together becomes a hard optimization problem, which is infeasible to solve. But what we find is that by just focusing on units, we can actually get away with constructing one data structure which represents the complete search space, and then we can just algorithmically search for the fastest implementation, which is of course much simpler than what general purpose compilers do. Okay, so let's look at how we actually construct this search space data structure. So the first part of the data structure that we build is for the memory layouts, and here we do something quite simple. We just take each tensor and we duplicate it for each valid memory layout. So in this case, just channel major and channel minor layouts. And yeah, in practice, we have a lot more layouts here, but it's just for illustration. Then in the second step, we decide how we map the logical operations from our input graph to something that we can execute on a GPU. And for this, we wrote a set of GLSL computators, and each computator has a set of valid parameterizations, and it defines a graph pattern. And a graph pattern essentially defines which logical operations can be implemented by this computator. And to give a quick example here, for a convolution computator, we could define the graph pattern like this, where we have a, where this right here says I can take a tensor of any layout as an input, apply a convolution operation, and then this will produce a tensor of any other layout. And what we can now do is actually quite simple. We can just search for all patterns of this graph, and then for each match, we just introduce an edge to a new graph, which represents one possible parameterization of this shader. And the idea here is that in our new graph, each compute edge now represents a concrete compute dispatch that we could, in theory, execute on a GPU. Now, we just keep on repeating this for all matches of the same pattern. So this way we get even more of these implementation edges. We can also define larger graph patterns, like with a convolution and a activation. And the matching logic here works exactly the same way. So we again search for these larger patterns, and then we add these edges, which skip a intermediate tensor, which is exactly how we represent fusion in our compiler. We then just keep on repeating this for all possible matches of the same pattern, which gives us our search-based data structure. And here, just to get an intuition here, the green edge comes from a computator which implements a concatenation, convolution, and a activation function in a single dispatch. Okay, so yeah, this is our search-based data structure. The whole idea why we construct it is that if we now consider one possible subgraph of this data structure, which connects the inputs, so A and B, to the output E, it represents one choice in memory layout, what computators we used, what fusion decisions we made, and how we parameterize these shaders. Or in other words, it's one element of our search space. In the same way, if we look at all possible subgraphs which connect the inputs to the outputs, it represents all possible implementation decisions that we can make, or in other words, our complete implementation search space. Now the obvious question is, which of those is actually best? And there's something quite naive or quite simple that we can do here. Because each edge represents a compute dispatch, we can just execute them on a GPU. This gives us a latency, and we then just use this latency as a cost function for the graph. And if we have a cost function, we can, of course, just search for the fastest implementation. And this ends up being a minimum latency subgraph problem. This is NP hard, but at least for units, we can still solve this very efficiently in just a couple of milliseconds. Now, there's one assumption that we make here, which is that the inference latency of the complete model will just be the latency of the individual dispatches, or the sum of the latencies of the individual dispatches. And essentially what this assumes is that the latency of a dispatch is independent of what happens before it, and this primarily ignores caching effects. But what we find is that dispatches where caching matters are generally very small dispatches, and they don't have a lot of impact on the actual final inference latency of a denoising model. So making this assumption is generally fine, and of course we have to make it because otherwise we could not search like this. Okay, so to summarize, we build a search-based data structure which represents all possible implementation decisions that we can make. Then we execute it on a GPU. This gives us a latency, and then we can just search for the fastest implementation algorithmically. Now, there's one problem, which is that the search-based data structure is still quite large. So this is for OIDN. This is still around 500,000 edges, and then if we would have to execute all of them or benchmark all of them on a GPU, this still takes 8 or 9 hours, and nobody wants to wait 8 or 9 hours for the compiler. So we do one thing in between, which is that we remove edges or dispatches from our graph based on 2 heuristics if we think that they're unlikely to be competitive. And essentially we use 2 heuristics here. The first one is that we remove dispatches or unfused dispatches if there exists a dispatch which has more fusion. And the second heuristic is that instead of considering all possible parameterizations of a computator, we just run offline benchmarks across a couple of GPUs, and then from those we select a subset of competitive configurations that we want to try out. And there's a bit more going on here, so if you're interested in how we selected this subset, then just check out the paper. Okay, so with this, we now end up with our reduced search space. This is now small enough, between 5,000 to 6,000 edges, and at this point we can just execute it on a GPU and then search for the fastest implementation. Yeah, so this is how the compiler works, but at the start I also said that we would look at more optimized fusions. So let's do this quickly. So there are essentially 2 really important fusions for units, or units with direct prediction, which is fusing pooling and a preceding convolution operation. And the idea behind it is just by fusing those, we reduce the amount of memory writes that we have to do. And we also just get rid of one complete dispatch, so this greatly reduces the amount of memory traffic that we have. And the other really important fusion is fusing upsampling, concatenation, and a convolution. And it's the same idea. We just reduce the amount of memory traffic that we have by fusing upsampling, reduce the amount of reads that we have to do, and concatenation and convolution just gets rid of the memory copy, so it's obviously worth. And just by doing these 2 quite simple fusions, we can already improve performance by a lot. So with TensorT, this takes around 11 milliseconds, and then just by doing these 2 fusions, we can get this down to around 7 milliseconds. And we can see the same effect if we look at larger models. So this is for OIDN. And NVIDIA, we actually get really good performance with a speed up of around 1.5 compared to TensorT and the OIDN runtime. On AMD, it's a little bit less favorable. The reason for this is not that the fusion approaches don't work on AMD. It's mostly because we spent much more time tuning the convolution kernels themselves for NVIDIA architectures, and we didn't have too much time spent optimizing those for AMD. And on Intel, the story is quite similar. Still quite happy that we're able to beat Onyx by, the Onyx runtime by a lot, but the Intel OIDN implementation is actually very well written. It does the exact same fusions as we do. They just have a slightly faster convolution kernel. Okay, so if you like this and you want to try it out, you can find the source code and a release version on GitHub. The workflow that we propose is actually quite similar. So we still train our models in tools like PyTorch, then we export them to Onyx. From there, you can just execute our compiler. This gives you then we do all of this profile-guided optimization stuff. This just gives you a file afterwards, and then you can just a file with a list of compute dispatches, and then you can just execute those inside of your own renderer. We also implemented this for one renderer, which is VKDT, and here we just use this with a code generation framework where we generate C code, which then constructs a render subgraph. It's actually worked quite well, where we get this very reusable OIDN component. So if you also want to check this one out, then just follow the link. So in conclusion, we propose a domain-specific neural network compiler for units, which integrates directly with existing rendering engines. We show that for units at least, a unified search over this space is actually feasible, and this can still result in fairly competitive or practical compile times. And last but not least, we show that by just applying very simple fusions, we can already outcompete existing state-of-the-art solutions like TensorT. And before I end, one quick note about the big limitation. Right now, we only support simple units with direct prediction, but we're of course aware of more modern architectures like kernel prediction and transformers. We just didn't really have the time to implement those yet, but yeah, stay tuned, maybe in the future. Okay, then thanks for listening.
Any questions? Could you provide a little bit more details on what would change with supporting transformers?
Yeah, so for transformers, the big problem is right now we don't have a matrix multiplication, and there's a lot of if you pass Onyx, there's a lot of like few transforms, like squeeze operations, which essentially don't do anything, but they just change the view of the data. And parsing this in this framework is not very easy, because yeah, you need a very fundamental, like in our case, we enumerate enums, like we enumerate the layouts, but for this you would need a representation like strides and sizes, which currently we don't have. Maybe we'll also switch to something like this in the future, but yeah.
Any more questions?
Great presentation, first of all, and sorry if I missed it, but to what extent is your generated code using the hardware accelerators for like tensor cores and MMX and so on?
Yeah, so we of course use the corporate matrix extensions. You can also compile models for GPUs which don't have it, then we just fall back to other dispatches which don't contain the corporate matrices. But yeah, of course we support them, and we also try out a lot of different corporate matrix sizes, because interestingly it actually matters a lot which ones you choose on a specific hardware. And it's also not that the same corporate, like on NVIDIA we oftentimes have more than one corporate matrix shapes, but oftentimes we get the best performance by just mixing them, or for example using for 32 channels we use one corporate matrix shapes, but then if you have a convolution with 64 channels you suddenly end up using another one. So yeah, we try a lot of them out. Yeah.
Any more questions? Okay, maybe a quick final one. So you mentioned that it's not really performing at top speeds on AMD, right? So how much time would you have to spend to kind of optimize for this framework for a different architecture, be it AMD, be it Qualcomm, whatever?
Yeah, so if we want to see the similar speedups that we see for NVIDIA, It's basically just a convolution kernel which is missing. So between NVIDIA and AMD, there's slightly different styles how you implement those. For some of them, you have to go first from global to shared memory and then into corporate matrices. And these tiling sizes that you choose here are slightly different. So if we would spend the same amount of time, and maybe for NVIDIA, we spend around a month optimizing these convolution kernels. So if we spend the same on AMD, hopefully we get similar performance as well.
Okay. Thank you. Let's thank the speaker again. Okay, this concludes the second session. I think we have a coffee break right now.
Hello? All right. Our next session will be the first keynote. It's going to be Patrick Cozy and Sean Lilly, but unfortunately, Patrick Cozy's plane was delayed, so the talk is going to be handled pretty much entirely presented by Sean here. So complex models, simple solutions will be what they present. So I'd like to turn it over to Sean. Thank you.
Just waiting for the slides to come up.
Display. Give me 2 seconds. Let's try this guy. Nothing. Nothing. What is no. Still nothing. Okay. One second. Let's see.
Do you have another laptop I could try?
Yeah, I'll give you one in a second. You have a USB stick?
Yeah, it connects with USB-C.
Okay, give me 1 second. I'm just going to. Move that laptop for me.
Can I just try my other laptop? Yeah, you can. Okay. Even this one isn't? Yeah, that was it. Yeah, let me grab it. Yeah.
Oh,
Or it's on my other
It's on that
computer.
side. Yeah. Need a dongle? Right.
Okay.
This guy?
First one. Yep. Enable content. Oh, is it possible to do the extended display?
Just give me 1 second. Let me. Do you know how to put the?
Wonder if it's
Oh, you want to extend the display?
yeah.
Gotcha.
Oh, I was hoping it would show the slide notes. Well, maybe, yeah, I can actually probably see the slide notes.
I don't even.
Okay, I think that's good enough. Okay, I think we're back. All right, so yeah, I guess that's the second technical difficulty today, plane flights, and then AV stuff. Okay, so I'll be talking about complex models, simple solutions. This is basically the evolution of 3D tiles. We've taken a lot of computer graphics techniques and applied them to 3D tiles over the years. And I'll give overviews of a bunch of these techniques and also some history of 3D tiles and how it's shaped over the past 20 years. So first about us. So I'm sort of speaking for both of us today, but I'm Sean Lilly. I joined the Cesium team in 2015. That was actually the same year 3D tiles was announced. And before that, I studied computer graphics at Penn, where actually I had taken Patrick's course. He taught the GPU programming course there. And then in terms of Patrick's background, he's been involved in sort of the 3D space for a very long time, and especially like the virtual globe space. So I think it was 2010 he wrote 3D Engine Design for Virtual Globes. It's a hardcover book. And then WebGL Insights a few years after that, and also OpenGL Insights. And now he is involved with a nonprofit called Create Access, which works with students to get them introduced to 3D creation tools. So examples include like scanning some data and bringing it into Unreal Engine, learning Blender, things like that. So this is a quick promo video of, this one might not play because we had a whole transfer situation, but this kind of shows some of the types of data that we work with. Basically, our domain is massive 3D geospatial data sets. So here in the background, you can see Cesium World Terrain. In the foreground is OpenStreetMap 3D buildings. And then we have a bunch of other open data sets, as well as people bring their own data to our platform. But the general theme is that these are massive data sets, 3D, and we sort of want like a common solution for rendering all of them. So in terms of the story, so it's really a 20-year story. So Patrick did a master's thesis in 2006. That's where he first started to look at the ideas of how to render large-scale city models efficiently. And then he applied a lot of those techniques to building Cesium, which is an open source WebGL-based virtual globe engine. And then that became open source in 2011. And in 2015, 3D tiles was announced and also became an open standard, and eventually went through the OGC community standard process, where a lot of other geospatial standards go through. And it's built on GLTF, which is a Chronos standard. And then 2018, just kept growing the developer platform. Cesium eventually spun out of the company that we had started from and became a startup. And then we were acquired by Bentley Systems in 2024. And now we're working on the next generation of 3D tiles and in globe rendering. And yeah, it still feels like early days. I'll kind of present some examples of things we've done already, but also future ideas for what we'd still like to explore. So this is a throwback picture of, on the left is Patrick's class at Penn. And Norm, overall this talk is dedicated to Norm Badler, who was our professor at Penn. And he was an early pioneer of computer graphics. He started the computer graphics program at Penn in the 70s. And is a SIGGRAPH pioneer. And he recently passed away, but we have a conference room dedicated to him, and we have, he has such a large body of students who are following his work. So it's, yeah, this is dedicated to him. So this is a look at Patrick's master's thesis. So back then, GPUs could handle about 10 to 200 million triangles per second. For example, like a Boeing 777 model would have maybe like 350 million polygons, which is still pretty big, but it's not maybe as big as now that we're seeing. And then all of the Google compressed satellite imagery was 70 terabytes. And I think now both the satellite imagery and also the 3D models from Google are definitely in the petabytes range. So the amount of data has only increased. So even if hardware is increasing, data is also increasing, and we still need specialized algorithms to render all this data in an efficient way. So then from master's thesis, where some of these initial techniques of like hierarchical level of detail and culling were being researched, fast forward to 2015, where a lot of them were being brought into 3D tiles. So now we're dealing with a globe engine where we care a lot about precision. Our roots are in aerospace and tracking objects and time dynamic data. So we care about outer space, but also subsurface, below the Earth. We care a lot about precision because the Earth is like 6 about 6 million meters radius, which is not very, like when you're trying to represent that with 32-bit floats, it loses precision pretty fast. And double precision isn't necessarily a given for hardware. We also have a free roaming camera, and everything is completely programmable in CSIM-JS. So you don't know exactly where the camera's going to go. It could go, you could either be using the mouse controls or have it be programmed. So we need something general purpose to handle this. And then also, there's a lot of real-world content that's out there. And we started to notice some data trends. So first, we noticed that there's a lot more open data being released, and it was getting larger and larger. And it wasn't just one type of data. We saw 3D buildings, point clouds, vector data, instance models, photogrammetry. All this data was starting to come, like, a lot of it was open, and then people were coming to us and asking, like, we have these massive data sets, but we don't know how to visualize it. And we had that theme across all these different types of data. It's also non-uniform. Like, some of these, you might benefit from more clustering approaches. Some of them, maybe it's fine if it's a quad tree or an oct tree, but it's not necessarily one size fits all. And then semantics. So we want to carry forward any of the properties that exist in the data. So the buildings might have like who owns the building or the height information, things like that. We want to preserve that all the way through. So the current, at the time, the current geospatial landscape was mostly focused on a 2D approach or a 2.5D approach, where you had the whole world, you had like a double-headed quad tree, and you sort of just subdivided evenly. And so that was sort of the state that we were working with then. But we realized we had to evolve from this 2D approach. So that's essentially how 3D tiles was born. So traditionally, 2D tiles, we call it 3D tiles. And we enabled a bunch of different types of spatial data structures. So it wasn't just 2D quad trees. This was now full 3D bounding volumes that could be subdivided really however you like. As long as you maintain spatial coherence, that you could design any sort of tree structures that you'd like. And so since then, we've received a lot of adoption of 3D tiles. And I think a lot of it is due to the fact that it is itself an open standard and is built on open standards. So 3D tiles is an open standard built on GLTF for the tile content, and that's an open standard through Khronos. And we've seen just this huge adoption curve over time, where initially 3D tiles was just supported in CSIM-JS, but then even early on, we started to see it adopted by other 3D engines, mostly on the web at first, but then gradually also game engines started to adopt 3D tiles, especially around like 2020, 2021. Unreal, Unity, and then Omniverse, and a bunch of other platforms started to adopt 3D tiles, and it just keeps on growing. So for today's focus, there's a lot to talk about in terms of 3D tiles. There's the tiling pipeline, like how we take the raw data and produce 3D tiles from that. There's also the cloud serving architecture that we have. Then there's the runtime 3D tiles engine. So given a tile set, how do you select the right tiles to render? And then there's the actual rendering engine. How do you interface with WebGL or your graphics API? This talk will be focused on the runtime 3D tiles engine, which is good because we actually don't talk about this too much, and it's cool to show the evolution of especially like CSIM-JS's 3D tiles engine. So we will be building 3D tiles from the ground up. There's a lot of concepts that go into it. In fact, a lot of them are very simple concepts, but I think putting them all together shows that there's like the greater whole from them. So initially, like base slate, you can just load a single model. And this is not a particularly large model. This is just over 1 million triangles. But there still is like this little lag time when you load it, just waiting for that GLTF to just load onto the screen. And it probably is rendering more triangles than we need. Some of the triangles are going to be behind us. Some of them in the distance there's going to be a lot of triangles occupying the same pixel. And then quite a bit of texture memory for our current view. So we can definitely improve on this. And the first obvious thing is to introduce hierarchical level of detail. So HLOD, hierarchical level of detail, basically has two main components. The first is you need some sort of spatial subdivision, and you need a concept of geometric error. Geometric error meaning like this tile has this error compared to the ground truth data. So when I exceed an error, I can then load my children. In terms of spatial subdivision, as I mentioned, there's a bunch of different data structures you could use: quad trees, oct trees, KD trees, other types And then geometric error, there's a few different ways to calculate geometric error. Often it depends on the source data. Here's an example, Hausdorff distance. This is what we use for terrain. So it's the max of the minimum distances between two surfaces. If you're dealing with point clouds, you might choose something like an average interpoint distance. If you're doing 3D buildings, you might select, you might try to reach a triangle threshold, and then the next building that doesn't fit into that threshold, its diagonal length would be the geometric error of its parent. And it's very flexible in terms of deciding what geometric error you'd like to use. At runtime, geometric error is then converted into screen space error, and this is based on distance to the bounding volume and the field of view and other metrics. But essentially, we're taking a geometric error and then turning it into screen space error, like the error in pixels. And if your current view is above a certain threshold of pixels, then you should load your children and render those instead. And now, with those two pretty simple concepts, we can actually already start to load 3D tiles. So the most basic 3D tile selection code looks like this. You just compute the screen space error based on the camera and the geometric error. And then if the screen space error is less than some maximum screen space error, then you select the tile and you render it. And you recurse over your children. So this is additive refinement, meaning you have some data in your parent tile, and then you load your children tile, and you render both simultaneously, like you're adding data to the current view. Replacement refinement is similar, but instead of rendering your parent and children simultaneously, you replace your parent with your children. And it's just a simple modification to this function. So adding these, we now have a faster time to first render. We've cut it in half. We've also cut the number of triangles in half. We've also cut the texture memory in half. And for much larger data sets, there would be a much greater difference in these numbers. And now we have multiple tiles. So instead of a single GLTF, we have multiple GLTFs. In this case, it's structured in an octree, but you can see all the GLBs over there. And then on top of that, so the source data doesn't necessarily fit in memory. The example I showed did, but there are data sets that are terabytes or larger in size that are not going to fit in RAM. So you have to have some sort of memory budget. In CSIMJS, our memory budget is 512 megabytes, and we have a least recently used cache. So every frame, we move the sentinel to the left, we start selecting tiles, and those go to the right of the sentinel. If a tile wasn't selected, it stays to the left. And then at the end of the frame, we look at the tiles that are still in the LRU, and we basically go from left to right and start to unload them until we meet our memory budget. And now, you could technically exceed your memory budget if you haven't yet exceeded your, if your screen space error hasn't been met yet, you can still continue to load data, or you can reduce your screen space error in order to meet the budget. You can take either approach. All right, now I'll start to touch on some of the tile selection optimizations that we've implemented. So the first sort of obvious one is frustum culling. So here we get 30 to 40% less tiles rendered just by culling things that aren't in the frustum. But we can add some optimizations even to this technique. So the first one is hierarchical culling with the children bounding volumes. So in this case, instead of, like in the picture here, the camera frustum might be intersecting the parent tile, but the parent content isn't actually visible. So it actually makes more sense to check at least if one of the children is visible before selecting the parent tile. And depending on the type of data set, you can get 8 to 22% less tiles rendered just by this very simple technique, which doesn't really add too much CPU overhead either. So it's a very nice win to load less tiles. Also, a very geospatial focused one is horizon culling. So this is checking if a tile is on the other side of the globe. So the globe is acting like an occluder. And you can pre-compute like an occludee point, which basically, if that point is not visible, then you know the whole tile is not visible on the other side of the globe. And so for this one, we see 5 to 30% less tiles rendered. And in the pictures on the bottom, you can even see how this impacts like the frustum size. So on the left, we don't have horizon culling implemented, and we have 43 tiles loaded. And the camera frustum is much larger, which may also lead to less precise results in terms of like the geometric jittering and all that. But then with the horizon culling, you can get a very tight range. And then the other occlusion technique, which is more standard, would be just GPU occlusion culling, so doing GPU occlusion queries, where you have, for example, and we've implemented this in Unreal, where you like use a depth-only prepass, In our case, though, we're testing the bounding volumes against the depth instead of testing the geometry itself, because we want to test the bounding volume, and if like no pixels pass the occlusion test, then we don't even want to load that tile at all. We don't want to even make a network request for it. And so we actually have two choices, though. So if a bounding volume is completely occluded, we have the option to cull the tile, just not render it at all, or we have the option to select it, to render it, but to not refine it, so to not like continually load its children. And both have different benefits. The second option is nice if your camera suddenly moves and now like you would see holes. This avoids seeing holes in that case. And here's a fly-through of sort of a city data set. And on the right is the amount of tiles that are loaded compared to like the occlusion culling with and without. All right, now, so we talked about culling. We'll also touch on techniques that help adjust the screen space error. So the first one is fog. So this is also somewhat geospatial focused, but could be extended as well to other domains. This is the idea that like in the distance, you'll likely have fog, and you won't be able to see those tiles as clearly. So it might make sense to to increase the screen space error for those tiles. So in this example, we got a benefit from 327 tiles to 228 tiles without too much visual difference. In fact, it might even look better just because it's more realistic. And you can see the tiles that were culled in purple. So you can both increase the screen space error and also start to cull tiles that are completely in fog. We've also looked at like approaches that involve the camera. So if the camera is moving, say you're going from you have a camera flight from one city to another, and the camera's moving at a pretty fast pace, it doesn't necessarily make sense to load all the tiles at the full detail that you would normally render them. So in this case, we actually increase the screen space error during the camera flight, and you have essentially a lower resolution version as you're flying. And then once you stop flying, you then have the original normal screen space error. And another optimization on top of that is to cancel requests for tiles that are no longer in view. So we might have made some requests for tiles, but by the time they come back to us, they're not going to be on screen. And so we should just cancel those requests. And that's fairly cheap, like for web browsers to do canceled requests like that. And overall, the results we're seeing are 27 to 49% less tiles loaded during those camera flights because of these two techniques. Another technique that we looked at is called foveated screen space error deferral. So this is kind of more of a priority function. So you might have two tiles that have the same screen space error, but some of them might be more perceptually important. Like they might be closer to the center of the screen, or they might just be deeper in the tree, so maybe they'll be higher detail. And so we have a prioritization metric, which involves a few different factors. So the first is the depth in the tile set, like what level in the tile set it is, also the distance to the center of the screen, and then distance from camera. And we also have, in addition to the priority metric, we also have this concept of deferred tiles. So tiles that are pretty low priority on the periphery of the screen are loaded after in a second phase. So we load all the important tiles first, and then those secondary tiles. And so what we've seen from this is the perceptually important tiles load 2 to 2.3x faster through this technique. And then another camera sort of trick is that if we know the destination of a camera flight, we can just preload the tiles in that area, and they'll be loaded right when the camera arrives there. All right, and then another topic, a separate topic, probably one of the bigger topics, actually. I won't touch on it too much, but I'd say in terms of research areas, this one is big. So this is level of detail skipping. Sort of the fundamental problem with hierarchical level of detail is that, well, it's not necessarily a problem, but if you want it to be fast, it's important to be able to skip tiles to load the high detail as soon as possible. There are a few different approaches, and they all seem to have certain drawbacks. Like some of them will have holes. So you might load the highest detail data, but then as you zoom out, there's nothing necessarily to render anymore if you haven't loaded the parent tile. And then the other approach is you could try to render the parent and the children tiles simultaneously. Naively, you'll have overlap artifacts like on the left, But in CSMJS, we have a technique that involves using the stencil buffer, like writing the priority as the stencil value, and then so it ensures that like tiles that are like deeper in the tree always render above tiles that are like higher in the tree. And that works pretty well. There's some artifacts, but yeah, it's one potential solution. I think there's possibly more for this. So here's a quick left to right comparison of with level of detail skipping and without level of detail skipping. I believe it's on a throttled connection too, which is why it's pretty slow in both cases, but the left side resolves much faster than the right side. And overall, just less tiles loaded, and it resolves much faster. Okay, now we'll jump to another set of techniques focused on tile content optimizations. So this is where we start to leverage a lot of the work that's happened in the open standards community, like all the mesh and texture compression techniques that are out there. So, so first we're going to look at Draco. That's a geometry compression library. And so on the left we have 3D tiles lossless with gzip. The tile set size is 738 megabytes, and the load time is 18.9 seconds. And on the right, with quantizing to centimeter error, we're seeing a tile set size of 149 megabytes and load time of 10.5 seconds. So quite a bit smaller tile set size and faster to load. And here's a point cloud example. So kind of similar numbers, maybe not quite as good as the mesh example, but we're seeing 1.83 gigabytes to 0.64, and then load time from almost 10 seconds to about 4.5 seconds. MeshOpt is another technique that's out there. Similar to Draco in some ways, it's also based on delta encoding, and usually you have pre-quantized data. So we did a comparison of lossless versus Draco versus MeshOpt for this point cloud example. We're seeing pretty similar results, I'd say, for Draco and MeshOpt. One other advantage of MeshOpt, though, is that at least this is, in terms of GLTF, MeshOpt can also be used to compress not just like your vertex data, but say you had instances and you have instance translations, rotations, scales, it can be used to compress those as well. Really, MeshOpt is like a very general purpose compression library, which is nice. And then finally, KTX2 and Basis. So this is a format that can transcode to GPU compressed formats. So you can spin up a web worker and decode it to whatever compressed texture format your device supports, and then it stays compressed in GPU memory, unlike PNG and JPEG, where you'd have to decompress it to raw RGBA 8 values, and that's, in some cases, 8 times larger in GPU memory. And we've also seen, even though compared to JPEG, it's actually larger on disk, but it's 5 to 10 times faster at load time, pretty much just because there's less GPU data transfer, because the data is about eighth of the size, like after it's been through the web worker and decoded. So this is a really big win for us, especially a lot of photogrammetry models that we receive, I'd say are primarily texture data more so than geometry. And so to have KTX2 is like super, super big for us. All right, and then some more techniques. So batching. I think I mentioned earlier about we want to preserve like the semantics and the properties that came with input data. And so we have like all these individual buildings. Naively, you might render each building as a separate draw call, but we batch them together into a single draw call. We encode a feature ID attribute, and then that allows us to be able to individually pick those buildings and look up the properties that are associated with them. And also instancing, so we use GPU instancing, translation, rotation, scale, and also the IDs to retrieve the properties. And then some other optimizations. So the standard like vertex cache, overdraw, vertex fetch optimizations. Those can be done as a pre-process when you are producing your 3D tiles. And then for the pick pass, we render to a smaller canvas size, or really a smaller region of the canvas. And then we still have to do the tree traversal, but we do a much narrower frustum that just covers that 3x3 pixel region. And that reduces the amount of traversal time. And then for any sort of geometry or texture compression, the decompression happens in a web worker. So looking at future ideas, so one thing is everything I talked about, except for maybe like occlusion queries, are supported in WebGL 1. So we've kind of put a lot of work into sort of like a pretty, like, honestly old like feature set, and we're still in the process of sort of thinking about WebGPU and like how to upgrade CSMJS to use it, and also some of the techniques that we could take advantage of now. So one of the first ones is we should probably be doing culling, like maybe frustum culling and definitely occlusion culling on the GPU, and then doing multi-draw and direct to issue those commands without a read back to the CPU. And even though mesh shaders aren't available on WebGPU yet, I think there is a proposal, and we would love to have culling at a finer granularity on meshlets. And then some more ideas. So I talked about level of detail skipping. I think there's a lot of research to be done for how to avoid artifacts and holes while being able to skip LODs. Also, streaming time dynamic data. So everything I've talked about was pretty much static assets, but once you add the time dimension, now your priority function has to include like the spatial elements, the geometric error, but also now time. Like, do you preload in advance? How many? Yeah, it depends also, like, are you clicking play or are you scrubbing through a timeline? There's a lot of different ways a user could be navigating their time dynamic data. There's also potentially different types of screen space error that we could look into, as well as specialized traversals. We have just one generic traversal algorithm currently in CSMJS, but you might have a different traversal if you know it's an interior or you know that you're like on a flight path. And so that's something we should explore. And then portals as well, so like a pre-computed visibility set of some kind. And then some final ideas. So often when you refine from a parent to your children, you load all of your children. What if we could batch those into a single request? And also sort of the inverse of that, what if we could, if we had different requests, could we fuse them at runtime to reduce the number of draw commands? And then another idea is how do we morph between different levels of detail? Because it's okay to, like, there's some tolerance for like going from high detail to low detail and just having a snap, but it's nice to see a bit of a transition, and there's a few different ways to do that. So I think our sort of call to action for pretty much everyone here and the broader graphics community is how do we get to the next 10x? Like, I think we've achieved a lot with some of the techniques. Like, a lot of the simple techniques have brought us pretty far, but either what other simple techniques or complex techniques should we be looking at to make massive data loading even faster? So with that, I think we'll do Q&A, and I see Patrick is here, so if there's any questions, we'll be happy to take them. Thanks.
There we go. Does anybody have any questions?
Hi. Do you plan, or is it already in development, to have some kind of support for radiance fields?
We support Gaussian splats, but not nerfs.
Okay, interesting. So does that change anything about the kind of techniques that you're using?
Sorry, can you repeat that?
Does that change anything about the kind of techniques that you're using for the 3D tiles?
Possibly, yes. Yeah, we haven't thought about radiance fields too much, but yeah, I could imagine it would change things.
Thank you.
Thanks. Great talk. So in most of your use cases, the shading seems to be kind of baked, right? So are there any use cases for, let's say, where you would need a path tracer or anything like that? Because then all these frustum-based culling techniques are not directly applicable, right? Because
so if we like move to a path traced renderer, so we'd still have to build a BVH of some kind, and we'd still want to like we wouldn't want to load all tiles right away, so there is some CPU aspect of doing some sort of like traversal before it even gets to the GPU. So I think some of the techniques still apply, but I think I guess once it's in the rendering engine, then and in the GPU, it could be different. Yeah.
I mean, if the ray spawns around, right, you cannot cull stuff that's outside your frustum, essentially, right? You need to have some kind of representation there.
Couldn't quite hear, sorry.
Oh, sorry about that. So, I mean, if you aggressively cull, right, data outside of your frustum, but ray tracer still needs it, right?
Oh, yeah. Yeah, I think we'd have to have... Yeah, actually, that does complicate things. We've also thought about that in terms of shadows because, yeah, you'd want off-screen geometry to cast shadows. Yeah, that's in terms of, like, moving to a path tracer, I think that's a big thing we'd have to look into.
Thanks, great talk. So one thing that you mentioned earlier was that you have a level of detail with respect to the camera speed. How does that also engage with like the distance to the viewer? So there was a demo where you're like flying through the city, and I'm imagining that it's using a lower level of detail because the camera's moving. But like objects that are very close to the camera, you know, like the level of detail is very clear as you're flying through. Is that being taken into account? Like what's the balance point between visual level of detail versus this motion level of detail?
Yeah. Ultimately, at least in our engine, it kind of boils down to the screen space error. So something, I guess, ultimately, like when you're in a camera flight, you'd increase the screen space error, so you'd be loading less detailed tiles. Yeah.
Okay. I guess the thing that I was noticing in that one video clip was that like there were like overpass models or whatever that were like very obviously low level of detail. And is that just like a limitation of not being able to load the high level detail thing fast enough? Or is that also just like, actually, no, we're going to cap that as the screen space error? Like, that's okay.
Yeah, some of it could be. It could also be the photogrammetry data might have been just a little bit low detail in general.
Oh, okay.
But,
understood. Yeah.
Yeah.
Thank you.
Yep.
Anyone else? All right.
Yeah, so you know, coming from WebGL 1 to WebGPU is like many generations of like GPU technology improvements now are available. When you look at the WebGPU spec, are there things that you would still want more, or like things that are missing that would benefit, you know, 3D tiles or cesium specifically that are gaps there?
Yeah, like beyond what's existing in WebGPU today. Yeah. I think mesh shaders would be a big one. Maybe some sort of like bindless textures, possibly. Trying to think of others. Yeah.
Yeah. Thanks.
I guess I'll ask one. So in terms of the web use versus native, what do you think doing this on the web is costing you compared to if this were like a native implementation?
Yeah. I mean, JavaScript obviously just is a slower language than C++. I think, though, the web has a really good network stack, so we do benefit from that. The web also has less parallelism. Like, web workers are pretty good, but you do have to often transfer data. You can sometimes do shared memory. Yeah, so probably less control over the CPU is probably a major thing. And also, I think even once we get data to the GPU, I think the browser just has a lot more levels between the CPU and the GPU compared to native. Yeah.
Anyone else? Okay. All right, I guess let's thank our speaker.
Okay, thank you.
And I think that concludes things for today.